Thanks for coming, even though I'm sure that it must have been harder than yesterday to wake up. But it's the last day, and still very happy that the attendance is mostly here, or the attendees. Okay, so really now, if you haven't put your name in the list yet for the social event, please do it now, because someone is calling right now. So please do this, and well, then let's just hear Roy.
Oh, thank you. Yes, thank you all for coming, in particular because I realize that the topic I'm about to present is slightly further away from your everyday lives. But I still think it could be an interesting showcase of the kind of research that you as open source graphic stack developers allow us academics to perform. So what I'm going to talk about is motivating preemptive GPU scheduling in real-time systems. And added the need for better models. I will get back to that in the end. So first I will briefly introduce some terms that we use in the world of real-time systems, so that makes it easier for you to follow the rest of the experiments that I've performed. Then I will explain why preemptive task scheduling on GPUs is, in my opinion, a good idea. After which I will briefly touch upon the need for better models of the GPU in order to better use these devices in real-time systems. But first, real-time systems. And the first question, of course, everyone has, why do we care? Well, the answer is quite simple. There's a lot of companies at the moment focusing on autonomous robotics, autonomous vehicles, in particular the self-driving cars, seem to be developing rapidly. And they perform a wide range of calculations from classification of, say, traffic signs and traffic lights, to detecting lanes in a road, to detecting other cars and pedestrians and cyclists, etc. And all of these are image recognition problems. They are deep learning problems. And these kind of problems, they lend themselves to be performed in a massive parallel manner on a GPU-like device. Now what makes real-time systems different from throughput-oriented tasks is that we mainly care about bound latency. Of course, performance is interesting, power consumption we care about, thermal properties are all important, but unless we can bound the latency of a single task that we perform, there is no use in having a higher performing system. There's two terms that I would like to introduce first. First of all, worst case execution time. I think most people know that one. There also is the worst case response time. And to explain the difference between the two, you can see a little schedule on the slides here. And for T2, this green little area is the execution time of my task in this particular schedule. The response time, however, is the execution time plus the time it had to wait for the other task to finish. And what you see here is an example of non-preemptive scheduling. And you see that the response time of a task and its worst case response time also depends on the execution time of other tasks in your system. Speaking of system, we define in the real-time systems a system as a set of tasks. And here I'm following the sporadic task model. There are several other models. I'm only very briefly touching upon this. And every task in your system, we reduce that to a set of 3 parameters only. The cost of it, the worst case execution time. There is a deadline in the real world time, which describes when your task must finish at the absolute latest. And there is a period, which we define to be the minimal interval between successive job releases. I haven't said what a job is, but to draw an analogy with object-oriented programming, your task is basically the class, the definition. A job is an instantiation hereof that is actually executing on your system. So we speak about task releasing jobs with a minimum period of P. There's one more, utilization. Utilization is nothing more than the sum of all costs divided by their periods. And to give you a bit of an intuition, if on a single processor system the utilization of your task set exceeds 1, this means that there is more work to be done than we have provisioned time for. Hence, we can guarantee that we will never make, we cannot guarantee that we'll ever make our deadline. If the utilization is smaller than 1, then there are more parameters, and this is the problem that we call schedulability. Schedulability, I've described here. Given a set of tasks and a scheduling method, where I'm talking about, in this case, fairly simple methods, but the Linux scheduler is a scheduling method. So think fixed priority, earliest deadline first kind of scheduling algorithms, and the parameters that you need. So for fixed priority, the actual priorities that you've assigned. Can we guarantee for all tasks that they always make the deadline? Or in other words, for every task in a set, is the worst case response time smaller than its deadline? Now, I realize that these have been quite a few terms, so here I would like to pause for a second and ask if there's any questions about what I've just introduced. No? Perfect. Oh, sorry. Let's see if I can just do this Jerry Springer style. Is there a microphone somewhere? Yes, please. Thanks.
I had a question about period. Is period the required period for successive executions of the task, or is the period at which the thing is actually executing?
The period is a minimum in the sporadic task system. There is a different system which they call the periodic task system, in which they guarantee that your task runs every time units. In the sporadic task model, we assume that it responds to inputs in a system like you would have an interrupt and then do something, and this is the minimum time between two of these events. Does that answer your question? Sorry? Like, but not quite. Okay.
I have another question.
Yes.
For deadlines, does each task have a deadline, or is there just an overall deadline to complete everything?
Every task has a deadline. Yes.
Okay.
Yes. Every task is described as a set of its cost, its deadline, and its period. And the deadline is expressed as the number of time units after a job release. So if it's release at T1 and your deadline D parameter is 4, then it must finish before T is 5. So I promised to talk about preemptive GPU scheduling. On throughput-oriented systems, I don't think there has always been a very strong use case because a preemption takes time. I'll also talk about the amount of time in about a slide. And that time is not spent on doing actual execution. Hence, often it doesn't pay off to do preemption. For real-time systems, it's a very simple trade-off between acquiring a lower worst-case response time for your high-priority tasks, on the one hand, which is your benefit, and your downside is that you will likely pay a higher context switching overhead because the preemptive case of context switching requires you not only to store all the state that you have, so the OpenCL or OpenGL state, but also part of your register file and your local memory. I'm talking about the two extreme cases here, and I'm very sure that we can do smarter context switching. We can implement smarter context switching mechanisms. However, I'm going to show that even in the extreme case of full preemptive, where you have to store all your state, including the register file and your local memory, we still benefit from having full preemption. But coming back, I will answer this question first. And the question is basically reduced to, can the higher overhead that we have for context switching in the case of a full preemption, can it be justified by a lower worst case response time? For this, I've done a little experiment. And the experiment is very simple. We determine the schedulability, so whether we can schedule a task or not based on the algorithm that we used and the parameters. we generate random task set, we determine their schedulability, and we do that for both a preemptive scheduling algorithm and a non-preemptive scheduling algorithm. And then we went about this by first determining the worst case response time of a non-preemptive context switch, the context switch only. Step 2 was estimating a very conservative worst case response time of the preemptive context switch, and then we compared the schedulability for both. So step 1, NVIDIA has already helped us a tiny bit, because in their white paper they said that the Fermi pipeline is optimized to reduce the cost of an application context switch to below 25 microseconds. Unfortunately, we couldn't use Fermi because the driver stack that we use, the Nouveau driver stack, cannot change the Fermi memory clock. Sorry about that, it's still a work in progress. Besides, Kepler is newer, so we opted to take a variety of Kepler GPUs, different context sizes, different maximum memory bandwidth that they can provide, and then expose them to the exact same conditions under Nouveau, running on its maximum clock speeds with a firmware that we adapted. Nouveau uses a firmware to do context switching, and we adapted this to obtain the time that it takes to do this context switch. We took 20-minute samples of this context switch per run, so per GPU, of a system that was running a resolution of 1600 by 1200 and a workload of a windowed open arena time demo. Now in this case the workload shouldn't matter much, because the time that we measured does not include the wait time for the graphics engine to actually pause. It counts from the moment the graphics engine is paused up until the context switch is finished. Hence there is no workload running while the context switch is running. I have to say, because we are looking at a real-time system, we used an intrusive measurement. We had to read out cycle counters, the maximum observed overhead by running this without measuring anything, so only taking 2 samples and then getting my final cycle count. We observed an overhead of about 224 nanoseconds, which in the context of a 25 microsecond context switch is about, well, just under 1%. Which I believe means that the measurements that we've done are fairly accurate. I've summarized them in this table. It's quite a lot of data. There's 2 points I would like to highlight right now. First of all, the average that we obtained, is still roughly about 25 microseconds. There's a slight spike at the GT640, but as anything, I would see this as a validation that Nouveau is doing the right thing, and that the target that we're aiming for is about 25 microseconds. Another interesting thing I've seen here is that on the low-end graphics cards, the worst case that we've observed is about 3.7 times as bad as the average. And that is something I will get back to later when I explain why we need better models of a GPU in real-time systems. But for now, I will continue with step 2 of my experiment. Because now that I have the average and worst case execution time, I want to estimate a conservative worst case response time of preemptive context switch. And here I made a very simple assumption that the worst case response time grows linear with the size of the context. This is very conservative, because the DRAM that we use to store the context to can guarantee higher performance when the amount of data that you're storing is bigger, if you engineer this well. But because I don't know exactly what the benefit of this is, we will take the absolute worst case, where I have the same DRAM bandwidth utilization as in the non-preemptive case, only for a much larger context. And this context grows with 256 kilobytes per register for every streaming multiprocessor, and for every streaming multiprocessor we add up to 48 kilobytes of local memory. So to give an example, for the GeForce GT640 that I listed in the table, which has 2 streaming multiprocessors, the total context size will be the original context size that we measured from the cards using a special tool I developed in our reverse engineering toolkit that I intend to merge later on, plus 2 times the context size of the register file size and the local memory size, adding up to a grand total of 676.2 kilobytes. Then I did a linear interpolation, and the numbers you can see in the table are about 10 times as large as well. That brings me to step 3. So now that we have a measured average and worst case response time for context switching and a very conservative estimate for the preemptive case, we can determine schedulability of random task sets. For this, I use a couple of parameters. First of all, I use uniprocessor earliest deadline first scheduling. Why uniprocessor if it's such a wide, massive parallel system? Because the entire parallel system is running the same task, is the assumption here. Hence, from a scheduling perspective, it's just one single processor that is doing a lot in every clock cycle. I generated 8.1 million random task sets using an algorithm that's called UUniFast, which guarantees that I generate task sets for certain utilization points that I wanted to target with a uniformal distribution. I recommend you to read the details if you're really interested in that. My task set, every task set I generated consists of 2 tasks with a period between 1,000 and 15,000 microseconds, which, according to the literature that I've seen, corresponds to medium to long kernels. And we use the numbers that are listed in this table. I made a couple of assumptions here. Because I was targeting embedded system, I took the parameters of a Tegra K1-like system, which is surprisingly similar to a GeForce GT640. So use the numbers that I've listed in the table. I've calculated the same numbers for a very high-end GPU, and the bandwidth roughly evens out the increased number of streaming multiprocessors. So the results would actually be quite similar. I assume that on a non-preemptive context switch, there's only one context switch per job, and I can assume this because I can assume earliest deadline first scheduling. And if you apply this scheduling algorithm in a non-preemptive system, the only point where you can do a context switch is after the end of your OpenCL kernel, after the end of your job. For a preemptive context switch, there are similar proofs in the literature that show that you can get by with assuming 2 context switches per job. The analysis that we do basically assumes that we always do 1 context switch per job in the non-preemptive case and 2 in the preemptive case. Hence, we can just inflate the size of a single task, the cost of a single task with a fixed amount of time. The results are shown in this schedulability graph, where on the horizontal axis you see the utilization of the tasks that we generated, and on the y-axis you see the schedulability for every single utilization point. And there are 2 interesting points I'd like to highlight in this particular graph. First of all, the green line, which corresponds with preemptive in the assuming the worst case preemption time, is still beneficial over a non-preemptive scheduling. It's a small difference, as you can see, and it depends a bit on the parameters of the task that you generate, but there is a difference. Furthermore, if we can bring the worst case context switching time down to, well, the average or even better, we can see a massive gap as well, improving schedulability even better, to a point that we cannot reach when we have only non-preemptive kernel scheduling. So in other words, to answer the question that I asked you earlier, can the higher overhead be justified by lower worst case response time? I believe that, well, between these points, yes, and if a system builder can actually choose between preemptive and non-preemptive scheduling, then absolutely. There was one other little point I'd like to make, and I didn't want to sweep that under the carpet. That is, yes, under the assumption of real-time task scheduling. The assumptions I made, and I explained that, is earliest deadline first scheduling, which is not common for a GPU-type workload, for a graphics-type workload. If we cannot assume EDF or fixed priority type scheduling, then we cannot give a bound on the maximum number of context switches that we do. Hence, this entire schedulability graph would look entirely different. In other words, we will need real-time task scheduling if we want to give guarantees on the maximum execution time. There was another point I made earlier on when I presented this table, and that is that the worst case is up to 3.7 times the average that we observed for the GT710. And I was kind of curious to find out why. Now, I'm not going to give you a full answer because I don't have this, but we did do a little experiment where we repeated the same measurement routine that we used to get the average context switches, only now with a different display resolution. So instead of 1600 by 1200, we also had the display resolution set to 1024 by 768, and we had a 4K monitor at 30 Hertz. And the results are quite interesting. So in this graph, I've shown a cumulative distribution of the samples that we took. And what you can see here is only the top 0.5% of all the samples, because the bottom half, it really just follows the same line and shows that most of the average is actually about around the 20-25 microsecond mark. And there's two things to observe in this particular graph. First of all, the tail, the absolute worst case that we've observed, happens in about 0.35% of all the samples, which means that if we were to assume that a context switch takes the full 80 microseconds for this particular GPU, then we are over-provisioning by 55 microseconds in 99.7% of all the cases. And that is a lot. What's more interesting is that the maximum that we've observed consistently shifted with the display resolution that we use. In other words, what we've observed is a performance interference effect where the scan out of your display, taking DRAM bandwidth from the same RAM that the context switching method uses, interferes with the performance, and as a result, what we've seen is that if you build your entire real-time system, for instance, and then decide, you know what, we have some spare CPU cycles, let's add a display and do some best efforts entertainment system or something, then all of a sudden you might not make your deadlines anymore on the high criticality systems, even though you've had all your priorities right. What I'm showed here is not necessarily that display scan-out will always make your context switching worse from a worst-case execution time perspective. Rather, it makes it worse from a worst-case response time perspective. However, doing these kind of measurements that we've done, unfortunately, it's very difficult to distinguish between what was my worst-case execution time and what was my worst-case response time. And what I would like to argue here now, before I wrap up, is actually that we need much better models of a GPU to understand their performance in a real-time system, like a self-driving car, to be able to better assess whether my task set is schedulable, to better assess whether my worst-case execution time is significantly lower than my worst-case response time. So to conclude, use cases for parallel accelerators in real-time systems. There is a couple of now. The self-driving car is a very big one. NVIDIA knows this. They released the Tegra, the Drive products. Autonomous robotics is the bigger picture, and I'm pretty sure that we will see more and more use cases in the field of real-time systems that is going to want to use these kind of massive parallel accelerators. Preemptive scheduling, I believe that improved worst-case response time that we can obtain outweighs the overhead that we have to pay for increasing the context size. However, if we really want to seriously use GPUs in real-time systems or be able to give any guarantees about the execution of tasks, I believe we need more control over the task scheduling policies, which often means we need simpler scheduling policies that are well analyzable. And I believe we need more accurate performance interference models to guarantee that my worst case execution time is not going to get too close to my worst case response time. With this, I would like to ask if there are any questions.
Given that the display interference is the significant bottleneck in your performance here, I mean, it seems like the GPU vendor would be very happy to sell you two.
Sorry?
It seems like the GPU vendor would be very happy to sell you two GPUs, one that is headless, that does your computation, and one that does the display parts.
Yes. Well, I've shown that the display is one major factor in increasing the worst case execution time.
Did you actually try disabling the display to see what the worst case response time would be without a display running?
I have yet to find a very good way of doing this in Nouveau, because to trigger context switches, I need a graphics a graphical workload. And doing that headless.
But you could turn off the redisplay, just make the monitor go blank.
No, I haven't tried it. Is the
Okay.
short answer. It might give some interesting data points though.
Yeah.
But seeing the shift between the different resolutions was already a very interesting.
And the other thing is, have you tried playing with the FIFO parameters that do the display refill to see if you can actually, because sometimes the refill parameters are tweakable. I don't know about a Nouveau, where you could actually change the amount of data that's being reloaded when the FIFO goes empty, so that it would have a shorter burst on the memory bus. I wonder if you could play with those. I don't know if those are configurable.
I believe it is configurable. We unfortunately do not know how or why. This would probably be part of the models that we actually need to do this reasoning.
Sounds
as well.
like you got plenty more research to do.
There is a lot of interesting data to gather. Yes,
Isn't that the whole point here?
absolutely.
Yeah, so you're measuring context switch overhead as the time from when the GPU goes idle to when it starts doing new work. Is that correct?
To when we know that the context switch routine is finished.
Okay. So there's a bit of a loss of efficiency or loss of throughput on either side of that, right? As you tell the GPU to stop and it starts draining work, and then on the other side, it takes a little while for it to fill up again.
Correct.
Have you tried to measure how much throughput loss is associated with that? Right. Whereas if you didn't do a context switch at all, it would just keep running at full throughput.
Correct. I believe that in the case of non-preemptive context switch, this is not necessarily a problem because the draining has to happen anyway. For a preemptive context switch, the draining should be fairly fast because you are storing all your state. Hence, you don't have to wait for your shaders to complete. You should be able to do that in the middle of execution. You might have to drain your pipeline. How long that takes, I don't know, but that is a fairly small overhead. That is not wasted computation, but rather executed before you might have wanted it. Not a simple problem.
Yeah. Okay.
Okay, if there's no more questions, I'd like to thank you for your time.
Yeah, I guess so. Okay, hello everybody. I will give power management update on Nouveau today. We'll talk a little about the work I done on power sensors. Then I will talk about the static power consumption of what I found on running Nouveau. I will talk a little bit more about GPU boost and what I've actually had to do to properly implement it or partly implement it with a Nouveau. I will give a general state of clocking overview about this, and we'll finish with a few demos. So I've added, or power sensors was initially added in the Linux kernel 4.6. There were still some issues because I didn't really pass the video BIOS tables right, so there were many improvements. It's exposed through the hardware monitoring interface in the Linux kernel, so user space processors can just hook them, let them read out. It's based on Martin's initial work, who actually worked more on the side on actually using those power sensors and calculating the power consumption from them, and I was more like working on the video BIOS tables and implement that in the code. It's supported on mid-end GPU starting with Fermis, so there's a high chance to actually find those power sensors because they are not on every GPU. What I find interesting in some workloads where Nouveau performs really bad, we had also a low GPU power consumption, and I think it could be, or it could hint at this, that we don't utilize the GPU enough, and this can hit, further improvement we still have to do is to move it on the PMU. PMU is a little chip on the GPU which is there for power management things, because currently it's done on the host, and this isn't. We should just move it because it's more useful there. So I will start with now clock gating on NVIDIA GPUs. You see in red, this is the old behavior or the current behavior on Nouveau for power consumption on GK106 and GM207 on 2 perf levels. And as you can see, if we start to clock gate the GPU, we can save some power. So usually, on the best case, I measured save of 25%, which is really good, I guess. It can actually also benefit some high loads, because if we manage to reduce the power consumption, this also means we can reduce the heat, and this leads to being able to run at higher clocks. It's work in progress for Fermi, Kepler, and Maxwell GPUs. And what I found out like 2 or 3 days ago, that if we don't do secure boot on the engines which we want to clock gate, there is no effect at all. So let's latch. Power gating is the second way to reduce the power consumption further. I'm not quite sure how much we can actually save, because we didn't actually manage to do it at all. We have already something, some use counting of engines in the kernel driver, so we might be able to just reverse engineer the entire thing and just use it. So I will now start with GPU boost. It advances the dynamic voltage and frequency scaling, and officially NVIDIA says for the 1.0 version it increases the clock until it reaches a specific power target. For the second version, increased clocks until reaching the temperature target, and it was officially added with Kepler's GPUs. But I was already finding some related video bias tables on Fermi GPUs. And we actually had to implement some GPU boosting stuff to actually be able to stably reclock the engines on a Fermi GPU. And most of the things related to GPU boost are indeed implemented in the kernel driver. Some might could think that there's actually some hardware bits doing this, but couldn't find that much about this. So, what I actually found out about how my understanding is about GPU boost is that it's actually more like we limit the voltage we can actually run the GPU at. So if you have a higher temperature, the video bias tells you to use lower voltages, and this leads to decreased frequencies. It's a bunch of file bias tables. I will talk later about, or now, after. The first table I will talk about is the voltage ID table, as we call it. It actually tells us how we have to voltage actually the GPU, because there are like different ways. One way is over GPIOs, where we just set some GPIOs to create a mask to select a specific voltage, and then we have the PWM based voltage controllers, which were added with Kepler, I think. And it also defines what voltage we can actually set on the GPU. Then there's the voltage map table, which is, in my opinion, the most important one related to GPU boost. It defines entries which can be chained together. It also defines some max and min voltage value per entries, and 6 constants we have to add to a formula, which is also chosen by the entry itself. These are the four formulas I could reverse engineer from the NVIDIA driver. As you see, the first one is a little bit complicated, but the second one indeed took some time to actually find out. I think you can see, yeah. The two important factors is, for one thing, the temperature. It actually affects the voltage this one entry maps to. And there's an individual chip calibration factor, also called SPEEDO by the NVIDIA Tegra driver. And yeah, the other both formulas aren't less interesting. So then we have a C-step table, where for one there's a voltage map table entry mapped to a specific C state or clock state, and yeah, I can show. Yeah, I could. It's a little bit difficult because for this to find out, I had to actually to modify the video BIOS and adjust the entries so that I could look at one constant at a time, and had to upload it on the GPU and let NVIDIA pick up the new video BIOS, and then I could just read out the voltage depending on the temperature NVIDIA was setting. And yeah, I will show the tool later in the demos with how I found it out. Okay, so back to the C-step table. It has actually also a list of all the GPC clocks we can set on the GPU, and it actually also defines for the P state, which are a little bit higher level than the C states, what we can actually set for a performance state. Then we have a PM mode table, which just defines a bunch of default clocks for each engine. Then we have the so-called boost table, but I think the name is a little bit wrong, but yeah, we don't know the official names. So it just contains clock adjustments for different engines, because we have different engine on the GPUs, and each get their own clock depending on the GBC clock. So there's also the virtual p-state table, where we actually got a bit of documentation from NVIDIA. It specifies the clocks with what the GPU is usually sold, because you see for NVIDIA cards there's a base clock and a boost clock, and those are defined in this virtual p-state table. Yes. I could actually show you how the wire BIOS looks like. And just to give you an overview about the voltage map table, I find really important. There you actually see the voltage map table as we can parse it, and you have some kind of max entries which just define an upper limit for the voltage. And then here you see the actual entries of the table, and there's a link, so they are chained together, and here you see the formula passed. Well, the formula isn't in the entry itself, so it's just a nicer way of seeing what actually is the result of the entry. And it's a little bit, there are a few entries. So, okay. This is an example on the GTX 780 Ti with a specific speedo value. The red ones are the max entries. We can't voltage above them, and what you can clearly see is that the maximum voltage drops depending on the temperature. So if you can, like for example at 40 degrees, you can select this C state to clock to. You can't if the GPU gets hotter. And here's an example with a GPU with a higher quality factor or speedo value, and you can also clearly see that now we are able to select a little bit faster C states, because the top ones are the fastest one, lower ones are slower. So actually it depends a little bit how good or how well the GPU was made to affect performance. There's also a p-state minimum voltage value, but this one isn't as important. It just defines if we select the C states with a lower voltage mapped to it, we just use the p-state minimum voltage. So the tool I was talking about is NV compare volt. It's simple reverse engineering tool. It reads out the hardware state directly from the GPU, so there is no interaction with the NVIDIA driver or any NVIDIA binaries at all. And it's just there to verify Nouveau's voltage algorithm against what NVIDIA does. I will show a demo at the end. So which are the actual problems we had to solve to stabilize reclocking on those GPUs? For first, we didn't respect those voltage limits at all. So even if the temperature was pretty high, we just used the highest one we had. We also tried to perfectly match the voltage to the actual hardware steps we have. So with the new voltage calculation, you can get any kind of value, and if we didn't find an exact match, we just failed. We didn't calculate the voltage at all, so we just were optimistic and used the lower bounds of the entries. And we didn't update the clocks when the temperature is rising. There's still no mainline support for this, but I'm working on it and should be there soon. So now to give an overview about the general reclocking state. We have hardware thermal protection up to GM10X. That's a feature of the GPU itself where it blocks the clock signals to the engines to lower the heat or power consumption, just to so the GPU won't be damaged by high heat. And there's also a threshold to shut down the GPU. Then we have fan management working up to GM10X. As we said yesterday, we can't do this on newer GPUs anymore. Engine reclocking works for most cards, up to Maxwell including. Memory clocking also works for most Tesla cards and also for Kepler and Maxwell. I also worked on getting the PCIe link configuring things in place because there's a really high benefit for prime offloaded systems. It actually matters a lot there. GPU boost is partly implemented for 4.9. So what's currently work in progress is the PMU engine load counters. They actually tell us how much load is on the specific engine, so we can react to this later. Memory clocking is worked on for Fermi by Y. And there's also a software thermal protection table in the video BIOS where it's stated like that if we go beyond 80 degrees, we have to clock down a little bit. And the table defines quite a lot of things, but I couldn't understand it enough to actually implement anything. Then there are also the power budgets on the GPU, which we are currently completely ignoring. Okay. So what's still missing? It's not that much important to actually adjust the clock reading code to while the hardware thermal protection kicked in, but I think it's a really nice task for new developers or beginners to get used to Nouveau developing, so I just listed it there if anybody's interested. Maxwell 2 fan control is missing. We really need this because otherwise we can't reclock those cards. There are some new bits for the engine reclocking, starting with the GK110 GPUs. There are also some issues with high PL Fermi and newer cards where we set really high clocks on the engines, and this doesn't work stable enough yet. There's this line buffer or so-called ISO hub, which we would need to implement flicker-free memory clocking on, I think, Fermi and newer. We actually need this. I'm not quite sure, but if you have, for example, also a multi-monitor system and you would reclock the memory clock, then you would have a lot of flickering while the reclocking is done. There are also new fan control video BIOS tables on Kepler and newer. Currently, Nouveau uses faster fans speeds than NVIDIA does, a little bit annoying for users. We have still to take care of memory clocking on the first generation Tesla GPUs. And related to Pascal, there's like everything different again, so this will be a lot of work. So for dynamic voltage frequency scaling, we have to look at policies, how we can dynamically adjust the clocks to the current workload so that we don't suffer in performance. So we have to talk about what is usable in general and how we have to deal with spiky loads which just have really short bursts of performance they need in their tasks. Then for getting this to work, we have actually to implement a monitoring about the engine loads on the PMU, which just would notify the host about if the loads are rising or decreasing, so the host can actually adjust the current set clocks. And we still need a various list of benchmarks so that we can verify that the implementation we write doesn't affect performance at all. So we need benchmark which at first measure the performance of a task with high performance needs. Then we have to test interactive tasks like desktop environments where the loads are indeed a little bit spiky, and also the same for web browsers. So, and I have also a working prototype for this I will show a few seconds or minutes. So firstly, NV compare vol2. For this I will, no, the wrong one. Oh, it doesn't matter. So at first I will just start the GPU with the NVIDIA driver and will set a few the clock to a higher stage. No, I don't see it. Ah, that's good. And then, was it here? Yes, this is the tool. There you see that it adapts to the changes on the hardware. You have the current set voltage on the hardware. We have here the voltage Nouveau would calculate for the given situation. There just here's an the difference about what we actually expect. Absolute, relative and absolute. Then here are the performance and clock states the GPU are actually set to, and then we have the temperature. So, and to give a little bit better thing, oh no, then I have to. We have actually also a tool to bring the GPU to think that a specific temperature is set. So I will just show this. Here. Now you see that I've wrote a loop which reduces the temperature step by step. And then you can see that the calculated voltage actually increases, and here we have a situation where we actually go above and this thing, the voltage NVIDIA set, and we see immediately that NVIDIA raises the voltage. So for the given temperature. And the reason why it's in this case better to have a lower voltage is that we actually round the value up to the next value we can set on the GPU on the step size. For example, on my GPU is something about 6.5 millivolts. And you see that there are several of these situations where we manage to find the temperature where NVIDIA would actually just adjust the volts. So yeah, that's for this tool. And this was also the way I tried to adjust the formula until I was sure that we indeed found the right thing, because it looks pretty well, because we already have, like, this is 46 microvolts difference, and we actually managed to properly detect situations where NVIDIA raises the voltage. So, yeah. Let's let. Okay, and now I will a little bit give a demo about my dynamic voltage and frequency scaling prototype. So, I just load Nouveau. Oh yeah, sure. So for this demo,
You'll need to increase the font size.
yeah, I guess so. So here's the normal P-state interface. It looks indeed a little bit different now. For the demo, I just forced the memory clock to the maximum because the prototype isn't really good implemented. It just works for the engines so far. We have the new interface for the boost clocks where we just set the maximum clock. So currently we have the lowest possible clock set, and yeah, I will just start a little game where we can clearly see pretty well how good it actually works. And here I have also some monitoring in place just to see. Oh yeah, it looks. Okay. I have some graphs here on the right side which show on the top the GPU voltage, then the temperature, power consumption, and the actual GPU load. And I will just go to a place with a higher... Oh wait. Sorry for this. I want a mouse. So, okay. Keep below hours. So, okay, now it works. So, as you can clearly see, I have in the top left corner an HUD with the FPS and the currently set core clock. And yeah, it just depending on the load, what clock we actually have to set for the GPU. And I think it works indeed already quite well. So there is an interval on the PMU set to check like every 100 milliseconds for the current loads, and just tells the host to reclock if it sees that the load is rising or is decreasing. So yeah. And as you see, the power consumption also reflects the currently set state. So yeah. Okay. Any questions so far? If you want, I can also try to show you some other reverse engineering tool we use in our work or things, but this is pretty time consuming, so I don't know if we would actually be able to. So, if there are no questions, I have still a third demo we actually wanted to show yesterday, but
There's one coming.
Ah, okay, nice.
So are you still having major stability problems when doing the reclocking, or has that been working better lately?
There is a difference between desktop system and laptop system. If we have a display attached, it tends to be a little bit unstable, and we talk about here maybe a crash in 4 or 5 hours. That's somehow the situation. On my laptop system, I was managing to reclock the issue for the GPU for minutes when I did around 500 to 600 reclocks a second, and this ran stable for minutes and hours without crashing at all.
Okay.
If I may add to this, I believe that the biggest source of instability when changing clocks comes from changing the memory clock. And this is one that is not clocked adaptively based on the load and the temperature, because that is a separate thermal domain. So doing this kind of adaptive engine reclocking based on the voltage and the temperature should actually be very, very stable.
Yeah, because there's no memory related at all. Yeah. Okay, then I can show you the thing Martin I think talked about. I think it's a really important feature, but yeah. We have here GPU, the LED control for the Titan GPUs or high-end GPUs in place. So I think it's a really nice feature. Maybe Martin wants to talk more about this.
Well, there's not much to say. It's just exported through the LED class. And so there are triggers for the LED, and the trigger that I was using here is the heartbeat one, which means that based on the load average, the heartbeat would be more or less fast. So yeah, it's just a funny joke.
Okay. No questions?
Hello, hello. Okay. Seems to be working.
Very good.
Okay, thank you. Okay, I think it's time to start. Good morning, everyone. I am Gustavo Padovan. I'm going to talk today about the mainline explicit things we've been doing inside the Linux kernel. I work for Collabora. Collabora is a consulting company specialized on bring clients to the upstream community. We work mostly on graphics, kernel, multimedia, and more recently we've been doing a lot of LibreOffice work. As for myself, I've been involved in the Linux kernel for a few years now, maybe 7 or 8 years. Before I've done some Bluetooth work, and the last 3 years are more. I've been focusing more on the graphics side of the kernel, and my main work now is exactly the mainline explicit things work. So here's a quick outline what I plan to talk about today. We are going to through a quick introduction on fencing, implicit fencing, explicit fencing. Then I'm going to talk a little bit about the Android Sync framework, which was the first explicit fencing implementation out there. Next, we are going through the mainline explicit fencing, what we are doing there. And finally, I'm going through the current status of each project we are touching. There is patch for Mesa, for the kernel, we've done some KMS Cube work as well, Jeremy Header Composer. So I'm going to talk a little bit about this. So start from the beginning. when we talk about fencings, we are basically talking about ensuring ordering between operations. So here we are on media or graphics. We are mostly interested on synchronize things between drivers, between your GPU and your display. You are interested in synchronize your buffers, so you make sure that you don't start writing on a buffer while it's still on the screen, and the other way around too. You don't start like displaying something that's still being rendered by the GPU. And when we talk about fencing, there is basically two ways of doing that inside the Linux kernel. We could do implicit fencing, where your user space is not aware of what's happening inside the kernel, and we could go for explicit fencing, where all the information about buffer synchronization is exposed to user space. So as I said, implicit fencing doesn't have any way to give information to user space, so user space can't know and can't interfere or anything happen on the kernel side. So that has one advantage that allows us to write like really simple compositors when we have to deal with buffers. We don't have like to deal with all the synchronization problems that may happen. However, we've been facing some issues. There are a few cases where your compositor can freeze and your whole desktop will freeze like for some time if you had like some delay on your GPU. I'm going like to show an example on what could go wrong, like a simple example. Let's suppose you have 3 buffers, A, B, and C, and we're going to use A and B to build C later, and send like A and B to go to the kernel to be rendered, and they finish at some point, and then you build C. You show your buffer C on the screen. However, if for some reason like your buffer A goes fast and buffer B takes some time to process, you'll be blocked waiting for B, and you'll block like for the time that B is being processed. You'll be blocked, and your desktop will freeze for some time. That's one of the issues we're facing with implicit fencing today. And here is where explicit fencing can help us, because it can bring this buffer processing information from the kernel, and it allows us to do some more smart decisions. Like in the case I showed, the composer could decide to go and display only buffer A and leave B outside, and take some old version of that buffer and display that on the screen, so you don't block anymore. Yeah, so explicit fencing allow us to do this kind of smart decisions on when compositing buffers, because it gives us a lot of information about the buffer status in user space. Yeah, here is just a scheme on how this is supposed to work. When we call exec buffer on GPU, we get a fence back on user space, and we can use that fence in user space to wait on it, or you can just pass directly to the KMS, and KMS would do the same thing, give you a fence back that you could maybe forward to GPU or wait on that. There is a few other advantages about having explicit fencing in the kernel. It's much easier to trace and debug your code when we have explicit fencing in the kernel, because there is now a way to know if your code like was stuck on your GPU or your camera maybe, or on the display before. With implicit fencing, if you issue like a page flip, there was no easy way. There was ways, but there was no easy way to figure out what was happening at the kernel level and at the buffer synchronization level. So explicit fencing can provide more information, more ways to debug your code. Another really good advantage is that Vulkans actually needs the synchronization, the explicit fencing synchronization mechanism from the kernel, because it's built in on some of its API, and also it's good for subbuffer processing on Vulkan. It's something I don't really know much about. I think there's a lot of Vulkan experts on their own, and they know a lot about this too. So now that I just like covered a little bit how explicit fencing work, I'm going to talk a little bit about the Android Sync framework. It was the first implementation to support explicit fencing. The kernel actually was on the Android kernel first, and it basically uses file descriptors to pass the fences between user space and the kernel, and between user space process if you need it. And the sync framework has three main elements. The first one is the sync timeline. That's basically to control the ordering of buffers. Then you have sync points, which is the actual fence, and the sync fence infrastructure to do the file descriptor passing between kernel and user space. So when we have the sync timeline, it basically has like a counter that you use to make sure you keep your ordering and your fences doesn't signal before they're supposed to. And you just like attach to your driver context, and you have like your timeline attached to a driver context. The sync point is, as I said, is basically the fence. They represent like some values on that timeline. And when you create your job, your GPU job, or display hardware job, you usually attach a fence to that, and your fence starts on the active state, and then when it's signed, go to the sign state, and if you need, there is a error state in case something goes wrong as well. The third and last element is the sync fence. It's basically a wrap that puts your sync point, which is your fence, inside a file, and you can use that file, then ask the kernel for a file descriptor, associate that file descriptor to the file you have, and pass that to user space. It also has the same kind of signaling, the active and sign state, and I think the error state as well. And one big advantage of sync fence is that we can merge fence together. So instead of sending many fences to the kernel, so the kernel wait on that, you can merge them together. Like in this case, you have one fence. The sync point 2 is on the first timeline, and the sync point 8 is on the second timeline. It doesn't matter if they're from different timelines. You can just put them together in a new sync fence, and send that to the kernel or to other user space process for them to wait on that. And there is three user space interfaces that we have on the Android Sync framework. They're quite simple. There's an interface to wait on a sync fence to signal, another one to merge the fences, and the sync fences you have. You give like two sync fences and give like a new and third file descriptor to merge with your merged fences inside it. And there is also IO control to get some information about the sync fence and the sync points inside that fence. So now on the mainline side, we've been like basing some of the work we've been doing on the mainline on the Android Sync framework. Other work is similar, so we didn't reuse like everything from the Android Sync framework. The first piece for explicit fencing that we had in the kernel was the fence synchronization mechanism that was added by Martin, I think about 2 or 3 years ago. It's a generic way to synchronize buffers inside the kernel. It's obviously not only for explicit fencing, but you can do for implicit fence or any other kind of synchronization you need to do between drivers inside the kernel. And the main structure in the fence synchronization mechanism is the structure fence, which provides all the basic infrastructure to deal with fence signaling and timelines inside the kernel. So we have a context associated with fence, and that context can do the same thing as we were doing with the sync timeline on Android. So you have a context, you have a timeline, and you can insert values and see if your fence is signed or not. And there is some API to actually sign a fence after your job is finished, and some other API to wait on a fence synchronously, the fence wait function. And if you need to do something asynchronous, you can just add a callback and be notified afterwards. So after we had the fence synchronization mechanism, the next thing we had to do was destage the sync framework on the mainline Linux kernel. It was added in 2013, but there wasn't many work done on that in the until end of last year, when we start looking at it and see how we could mainline all the Android sync framework. So, but after we had the insertion of the fence synchronization mechanism on the kernel, most of the things that the Android sync framework was providing wasn't necessary anymore. So we took it mainly for the file descriptor passing features. So like the sync timeline was something that was already done by the fence synchronization mechanism. The sync point which is exactly the same thing as a struct fence in the kernel. It's something we removed as well from the sync framework. And the last and the third element, the sync fence, we kept some parts, but we reworked most of it. So the sync fence actually became the sync file. We just did this name to remove some confusion and to actually state that we are talking about files and not fence. It's just a file that contains fence. Another thing we did was changing the IO control API, as at the time there was no mainline users, no upstream users on this framework. We thought it was a good time to go and make the API more future-proof, and so we add some new elements to the API, new flags fields that we could use in the future to extend the API without the need to break anything. The only user at the moment was of course Android, but there are currently patches at the moment on the guarantee Android to support the new API. They are not upstream Android yet, but I hope they will be in the next month or so. We also removed most of the internal kernel API in the sync fence mechanism. It's not a sync file, and we are using it strictly for passing file descriptors around. So there is now only two functions that this framework export. There is one to create sync files when you have a fence, and there is another one to get the fence from a sync file descriptor that you usually receive from user space. And when we work on this last function, we had a problem that if you get a merged fence from user space, we had to figure out how to deal with many fences and how to do this properly. So we came up with a new concept inside the fence mechanism. It's called the fence array. So in case you have a merged fence, like the sync file framework will not deliver you like a normal fence. It will deliver you a fence array, which is basically a subclass. So you can do all the API operations you are using for fences. You can also use with fence array, but it has the advantage of storing multiple fences inside that. It's the main use for that was, of course, the sync files, but there are also other uses inside the kernel now for fence arrays. One of the big advantages is that we can we can hide this complexity from having one or multiple fences inside a sync file, inside a sync file descriptor. So if the driver, like the case of GRM KMS, doesn't need to know if there is one or two or three or any fences inside the file descriptor, it can just use the fence that it receives. Doesn't need to care about how many fences are in there, and it can wait on those fences to signal. When all fences inside a fence array signal, the fence array itself signals, and you can proceed with your job. But if for some reason you need to know what's inside, and you need to check each of the fences inside, there is also ways to check if that fence is a fence array, and then there is a way to go through all the fences inside our fence array. Yeah, I think that was all about infrastructure to support explicit fencing in the kernel. The next thing we moved to do was to actually supporting that on the drivers, on GRM KMS, and on the GPU side as well. So on KMS, explicit fencing will only be available for atomic mode setting. We are not caring about any legacy API here, and the entire work has been done on GRM core. So drivers basically need to do nothing at the moment to support explicit fencing, and we had to basically extend the atomic I/O control interface to supporting sending fences to the kernel and receiving fences to the kernel. And we decided to name those fences in fences, the fences that we send to the kernel in this atomic I/O control, and the kernel has to wait on that before it proceeds with any scan out on the screen. And we also the fences we sent back to user space, we decided to call that out fences, the fences leaving the kernel. That are fences that the KMS creates when it receives atomic commit request, and that fence will signal when the buffer is on the screen. So for the fences that goes inside the kernel, we added a new property for the DRM plane infrastructure. So if you need to pass a fence for a specific DRM plane, you just fill the sync file descriptor in there, and inside DRM we have a new helper, a new atomic helper that can do all the waiting job for you. It goes to all planes in your request and waits for all the fences associated to all these planes to signal before it proceeds with any commit, any scan out. For the out fences, the semantics is a bit different. We have one sync file, one fence per CRTC. So in the kernel, we create a fence and associate to this CRTC, and later we create a sync file and a file descriptor, and we install the file descriptor on that file and send that back on the atomic request. And as I said, this fence signals on scan out, so that means the previous buffer can be reused, and the current one is on the screen, the one that's signed out. That semantic is a bit different from what Android was doing on the Android Sync framework. Here they were doing the opposite. Like when the CRTC fence was signaling, it actually meant that the buffer that's signed was free to use. But on DRM we decided to follow the same semantics as the page flip event signal. So we have the fencing like in opposite way from Android Sync framework. To get like the out fences in user space, the user space need to explicitly ask for that. So in every atomic request that it sends to the kernel, it needs to pass a new flag that we're adding during during mode atomic out fence, and we are trying to propose a new libdrm APR to do that for us. So on the rendering side, we have a similar mechanism to KMS, but with the difference that as the way they're implemented today, we need to go and support every GPU driver. So we need to extend all the exec buffers, IO controls. We need to add the sync files and fence supports to all drivers. Currently, there is some work in progress on Freedom. Actually, this mainline, I think, because Rob Clark sent on the last pull request the support for fences on Freedom. On i915, there is some work in progress, and I've been working on Virgil to add fence support in there as well. On Mesa, if we are going to support the same extensions that Android had for explicit fencing. So there is one extension to ask your GPU driver to create a fence for you, and delivers the fence back to you, so you can forward that or wait on that fence. And there is a second extension to do the other side, to ask your GPU to wait on fence before it proceeds with any GPU job. Just currently a work in progress, and Rob has been working on this, and we managed to get KMS Kube running explicit fencing, I think like 3 or 4 weeks ago. So we have like the full pipeline now on Linux. We have a proof of concept that everything can work with explicit fencing. And one final piece is the GRM Hardware Composer 2. Okay, that's used the Hardware Composer 2 API that was released by Google, I think last month or this month, I'm not sure. We are using, our plan is to use GRM Hardware Composer as the example user space for upstreaming these paths to KMS in the kernel, as this is a requirement from the community. So we are currently working on adding fence support in GRM Hardware Composer. There was some initial paths from Shampoo, and Robert Foss from Collabra is continuing this work, and he's also going for the fence support in there. Yeah, here's a quick summary of what we've been doing and what's currently going on. All the sync framework infrastructure, like the sync file and the software synchronization mechanism that is quite useful for testing, was already staged and is already upstream. The fence array mechanism, it's also upstream. We have paths for KMS and some handling drivers, but we are currently waiting for GRM Hardware Composer to be able to show off this working user space. Then we should be able to upstream this on 4.10, I hope. I think Mesa is just a matter to get everything upstream in the kernel. We could upstream Mesa. We've been also working on a bunch of tests for the IGT GPU tools. We have tests for the software sync validation framework, for sync files, and for in fences, out fences. I think we have more work to do in there, more cases to cover, but it's something we've been working on already. GRM Hardware Composer is also a work in progress, as I said. And one of the next steps that we're probably starting the next month is getting support for Wayland, adding explicit fence support on Wayland. And one of my next tasks after we are done with the GRM, I'm planning to go to V4L and see how we can do explicit fencing there and have our full media and graphics pipeline working. work with explicit fencing. Yeah, I think that is all. I would like to thank everyone who have been working on this. I mean, of course, not doing this alone. So there is all these guys. I think some of them are on the room. So yeah, thank to everyone that's been involved. It's been like a really nice work to do. So yeah, I think that was all. Thank you everyone. If you have some questions, yeah.
Hi, hello. I was wondering what is the difference between Android FD and your FD? Why there are two of them?
From Mainline and Android?
Yes.
It's basically the API. Like no, there is no main difference. We change the control APIs and you use like almost the same way. And another thing that changed was the semantics. So the GRM signs the fence when the buffer is still on the screen, and Android used to sign the fence when the buffer was out of the screen. But that was already fixed by Android on Higher Composer 2 and Surface Flinger. So I don't think users need to care that much about unless you implement on your own Higher Composer.
Okay, thank you.
So two quick questions. One is, I saw that you have, so you put up a fence merge entry point that takes two fences and combines them. Is there any sort of a fence multi-merge where we can do more than two fences with one ioctl?
Sorry, could you repeat?
So in terms of merging fences,
yes.
So if we have multiple fences,
merging fences.
Can we merge more than two fences at a time? Or do we have to merge them two at a time?
No, it's like only two at a time.
Okay.
Yeah, you need like to make like multiple calls to merge more than two.
Okay.
At the moment.
The other question is, so I understand that if you want to pass fences along from one process to another, file descriptor is obviously the way to do it. But if we want to use fences within a single process, is there a slightly lighter weight mechanism that doesn't burn file descriptors?
Well, for this mechanism, no, it's only file descriptors, but there should be other ways that I'm not aware of. Maybe there are some other people in the room that can answer that.
Okay, I'm just thinking about in Vulkan where the user can create semaphores pretty freely, and if every one of them is backed by a file descriptor, that might end up burning a lot of file descriptors in my process when we don't need to. I mean, obviously, if I'm going to send a fence to the window system layer, I need to turn it into a file descriptor before I pass it across the pipe. But if they're going to be using them for other things, it might be useful to have some mechanism of using them that doesn't actually burn file descriptors.
Yeah, maybe something you could look at as extension to this. Okay, thank you.
Okay, test. 1, 2. Sounds good.
Anyway, so what I'm going to be talking about today is a bit of the AMD DAL display driver, or at least that's what we used to call it. The team, what we do. Yeah, so the agenda is basically about DAL and the display solution team, that's what we like to call ourselves. Some of the design of the DAL 3 driver, a quick walkthrough of DAL 3, some challenges and takeaways if we get to that if you have time, and questions at the end. So if you've never seen DAL, it's basically a display kernel driver that's currently not upstream yet, but it's sitting in the AMD open source trees that Alex maintains. So it's free for you to check out if you're interested. So this is the team that we have working on the display driver. And that's quite a few people, but that's not just Linux. We basically do display across everything, across all the operating systems pretty much at AMD. We're all in Markham, Ontario, just north of Toronto. The main Linux guys that you'll see around on some of the mailing lists would be myself, Andre, Jordan, Elie, Eric. You'll probably see other names pop up too. Kind of to put some faces to names. So about DAL, a brief history. DAL, and I know this is not going to sound very pleasant, was named the display abstraction layer. That's fairly ancient. If you look at the date in 1998, is kind of when it started. So we're trying to get away from the name, maybe call it display core or something. So history for the display driver, and again I'm talking about display driver across all OSs. There was version 1 from 98 to about 2008 that dealt with the old DBI, VGA, LVDS stuff. There was C code that was architected for Windows 98. Then there was version 2, DAL 2, that came with Windows Vista, about 2008 timeframe, that started dealing with DP, HDMI, content protection, C++ code. It was also used in the AMD Catalyst closed source driver. I'm not going to share that code with you because I can't, if you're curious. Then onto that driver, we later retrofitted new concepts like DPMST or dynamic refresh rate, which was also used for FreeSync or adaptive sync. Hardware layer composition, at least on Windows. So that brings us to DAL 3. So now you kind of have a background how we came up with the name DAL 3. This is version 3 of the driver, so the name might still change. Basically, the idea behind that is the ecosystem, hardware, everything is evolving, and you need a new driver, or we felt we needed a new driver to deal with all these new concepts and where the industry is going. So there's the DRM atomic mode setting, and I think when we designed DAL 3, we kind of had some similar concepts in mind. Now granted, we might not be doing atomic quite correctly yet, but we're still working on that. Dynamic refresh rate hardware composition, where you have multiple layers. Managing shared hardware resources, where you no longer have resources that are dedicated per pipe, but resources that can be shared across different display pipes. And I think the industry is going for compression of display streams, wide gamut displays, HDR support, and we've heard some HDR stuff from NVIDIA at this conference. Anyway, DP 1.4, some really high resolutions are going to come in the future too, so we want to have a driver that's ready to deal with all of that. And we also, as a company, like to have a driver that allows code reuse across different operating systems. So that might include Linux, Android, Windows. And in addition to that, we'd like to do emulation with our code. So we're not running this in actual operating systems, but just run a diagnostic test suite that tests the driver, that tests our hardware, and makes sure we're good and what we're doing is solid. So there's been a lot of changes to accommodate the Linux kernel. I don't know if I want to say accommodate, but really this driver started development on the Linux kernel side. So that kind of meant we started out with C, we started out with Linux kernel coding guidelines, more or less. Again, there's probably room for improvement there. And what the team does, all the people that we saw, is basically provide end-to-end solutions on multiple platforms. So we just want to make sure if you have AMD hardware, the display works. You don't have to worry about it. And why am I here? Well, we'd like to share our expertise, our experience, our knowledge, our code with the community. We don't want to continue working in isolation in a closed source space. So DAL on Linux, mostly you know, there's DAL, there's the AMD Catalyst driver that had DAL 2, the previous iteration. It was sitting in user space, it was closed source C++ based, and it was really Windows-based architecture. And then legal wanted me to say AMD GPU Pro here. It's really AMD GPU. Any driver that's based on AMD GPU. It's a kernel-based driver, developed by C code, native Linux kernel support, and we want to enable early support of new ASICs on all operating systems, not just Windows. So a new ASIC comes out on Linux, you should be able to get maybe not quite the same support as on Windows, but something along similar lines, at least shortly after. So I've alluded to that. Some of what our team does is really working on specs and with the standard bodies. We care about display interoperability and work with display vendors to that regard to make sure any issue is fixed either on the display end, on our end, wherever it needs to happen. Compliance. And we also attend these events that are called Plug Test or Plug Fest, where different vendors come and they hot plug displays and make sure everything works fine. So now to get into the driver a bit, DAL 3 design. As I mentioned, it was kind of designed with multiple OSs in mind, and in that regard we have a display manager layer that deals with the OS stuff and a display core layer that basically deals with our hardware. There shouldn't be any OS specific stuff here, and this stuff should really just be dealing with, say, Windows peculiarities about querying for modes and all that, and on Linux reusing that stuff on DRM. We'd like to reuse as much as possible. We're not doing as much as people would like, but well, it's a work in progress. So this slide is a bit complex, but anyway, these are the objects, kind of how we think of the different things we're dealing with in the display system, surface or plane, targets, etc. But the interesting part I want to draw out here is the yellow stuff. That's how we abstract our hardware away. And I said abstract again, but basically that's how we want to think of our hardware. You have virtual hardware blocks, so these don't conform one-to-one to real hardware blocks, but they're more logical entities like input, output, pixel processing, transforms, like scaling something on the display, the CRTC, etc. Hardware sequences starts tying that all together in terms of hardware sequencing. When you enable something, hardware sequencer says we got to program these blocks in this order. And on top of hardware sequencer is, or along with hardware sequencer, we have a resource manager that makes sure we grab the right shared resources, hardware blocks, and put them all up in the right order. And it also cares about validation. Can we run this mode on that hardware? Can we run this configuration? Okay, the benefits of the DC-DM design, the display code that's OS specific and display manager that display managers or a specific display core that's just independent. So we can leverage hundreds of hours of testing of the display core across different platforms. I mean, unfortunately, or it is how it is, Windows has more users than Linux on the desktop space. So we can leverage that testing. We can also have our own diagnostic test suite, run our DC code class, and make sure that's all solid. And right now, we're actually doing quite a bit of testing on Linux as well. So there's manual, there's automated testing involved. So we hope that this common code base benefits everyone. Let's see, how are we for time? Yeah, I think this is good. So now that a lot of the history and high-level stuff's out of the way, I figured I'd give you guys a taste of the code base a bit. So these are pieces of code put together. You can find them in our source. This is basically going to be a walkthrough of a set mode. Atomic commit, where you set a theming mode on something. These are kind of the interfaces, at least how we initially designed it. Some of that might have changed. The slide's a bit old. So we can start here in DM atomic commit, and this hooks into the atomic function pointers for commit. We're setting up our atomic states, atomic functions, and I'm not the expert on atomic. There's other people that worked on that more in my team. We'll try and skip over that a bit. After that, we're going to basically determine the action that we want to take from the atomic state to see what changed and what we need to do. And we're going to create a new target and remove the old target for everything that's in the state. I don't know how things work on Wayland right now. We haven't tested that yet, but we're just working with good old Ubuntu right now. And when we get a commit, I believe that it's only the CRTC that changes that's in the state. So that's why we're doing this. This might change in the future. So we'll just add that to our new CRTC list, set that to enabled, remove previous target if that existed, meaning if we're changing the mode instead of setting a new one. And then we're going to iterate over all the CRTCs that are out there, gather up the targets, and give that to DC to commit. And that's pretty much all we do in DM to set things up. Once we're in display core commit targets, we're going to check if somehow the targets didn't change. We're just going to exit. Otherwise, we're going to start preparing for programming our hardware. So pplib refers to our power play library that deals with power management stuff. So raising clocks, lowering clocks, all that fancy stuff that the Nouveau guys had to reverse engineer. We're given it a nice library. You can look at the code too if you like. If we're taking over from video buyers, we're going to tell our display pipe that we're going to run an accelerated mode now and that the driver is going to program stuff. Then we're going to go into our hardware sequencer. So this is now hardware-specific code. We still try to share as much as possible, but this can be tied to a different version of the hardware. I'd apply the context. Did I miss something? Yes, I did miss something important, and that's up here. Validate with context. This function is named validate, but really what it does is it validates and it builds up a context. So it's really a built context with validation. In this case, validation shouldn't fail because we're an atomic commit and the validate happened before already, but we're building up our context here and we're using the same function. What validate looks like is something like this. We're adding our targets to the context, our resource pool. Here at the top, actually validating from surface set. Down here, we're then going to map the hardware resources. I'm not going to go into that, but we're going to figure out which hardware blocks we need and add them to the context. And depending on our ASIC-specific hardware requirements on what can be used, what can't be used together, and then we map the clock sources in a similar way to dealt with a bit differently than other hardware objects. Then we're going to do a validate attach surface, and this is probably going to build parameters instead of just validating. It's been a while since I stepped through that code. Same with map to resources. This one is actually called build scaling parameters. And then we validate the bandwidth requirements to see if we can do this without running into any underflow issues or other problems. Okay, so we're back in DC commit targets. We left validate with context. Now we're going to go and apply this context. So apply context again, we're in hardware-specific code, AC-specific code. We're going to check if we need to reset the pipe. If we do, we're going to reset it. Actually, all the pipes. We're going to iterate over all the pipes because we're still working on everything. Basically, all the displays that you see. Then we're going to check if we need to switch clock sources, if they change for whatever reason. Sometimes if you have the same timing shared between different displays, we want to use the same clock source, and then the displays are in sync. You don't, it's useful for some applications. Then we're going to disable power gating. So we basically ungate all the pipes to make sure we can actually program them. So this kind of goes it's along the line of calling TP-lib to apply a safe state. We want to get into a safe state so we can program whatever we want to program. And then afterwards, we're going to apply the most power efficient state. Same with the watermarks. So watermarks are used for fetching stuff from memory into the line buffer. We're going to set safe watermarks. We're going to see if we need to update or erase the display clock. That's what drives our display engine. And then we're going to go over all the pipes, and for each pipe, we're going to apply the context now. So now we're in a safe state, and we can basically do straight up programming. And that's what we're going to do. We're going to blank program pixel clock, program timing, memory input. That's where we read the surface from a frame buffer, etc. I'm not going to spend too much time on this. I'm just going to go into set blank briefly to show how we program registers. So in most cases, when I'm calling the video bias, we're just programming hardware registers directly. The way that's currently done is not very readable. We're still working on that, trying to use some macros to just make it more readable and easier to write, easier to understand. This takes up a lot of lines just for updating a register field and then polling on two fields. It's kind of wasted space. But it's not that important, I guess, in the grand scheme of things. So after that, we program more stuff, enable CRTC, output pixel processing for whatever format we're driving. Our link encoder, stream encoder, whatever drives the output to the actual display. Set a black color depending on color space. Do more enablement. I think at some point in time here we're going to trigger a link training, and we can probably still reuse some of the DRM functionality for that. We are not currently. Program a scaler, and then if everything went fine, we're returning. After we've programmed all the pipes, we're going to program the audio. Again, if you look in the code in another week, 2 weeks at a time, this is probably going to change a bit, but the gist is still the same. We're going to go over all the pipes that need audio and assign audio devices and program that as needed. After that's done, we're going to then set proper display marks for whatever we programmed from the context. We're going to switch clock sources. I'm not sure what this is doing here. Then we're going to, on all the pipes that have surfaces, we're going to enable memory requests to make sure we're actually driving something or putting something visible. And then TP-lib, we're again applying display requirements to set the most optimal power state. And with that, we're basically out of DC for the set mode. I'm not going to spend much time on this. Basically, what DM does next is pretty much check if we need to commit some surfaces or if we need to do flips. But if you're interested, you can go through the code and figure that out or play with it. This was just kind of to give people an introduction, to give you an introduction into the code. Challenges and takeaway. I'm going to just briefly mention one of the challenges that we have. So we often have to deliver features, and these features sometimes depend on common kernel functionality. In order to get that delivered on, say, a Ubuntu 16.04, which is still on the 4.4 kernel, we would have had to start on a feature a year ago, in order to get that in. I'm not sure how we're going to work with that, and if anybody has good solutions for that. I mean, we could always, generally our business units want us to deliver features much quicker than that. So we're still trying to figure out good solutions. If anybody has ideas, or
get your work done earlier.
Sometimes the spec's not done early enough. Sometimes the hardware's not done early enough and we don't quite know what we're doing ahead of time. So now feature turnaround becomes a year instead of a month. It's difficult for companies. If somebody has a good suggestion, I mean, starting out early is always a good idea, but it's not always feasible. Thanks. Okay, take away, and then we might still have a couple of minutes for a question. So DAL 3 architecture was designed with Linux in mind, actually started development on Linux, and was designed to be ready for future things that are happening in the display industry. We as a team are committed to Linux and we're willing to work together. That's still sometimes a challenge internally on how to get people out into the open, but we're trying to help us. Yeah, we're eager to also share our experience in the industry with the community. We're dealing a lot with displays, with specs, with vendors. We'd like to contribute. I know we haven't done a whole lot, and there's been a bunch of common DRM functionality that we could have delivered and could have helped with. So that's partially a question of resource and not having enough. And the default is always coming from a closed source team. It's easy to implement it in our own driver, we know it all. But we'd like to change that. I'd like to change that in the team. And we'd like to learn from you and contribute whatever we do. All right, questions?
Yeah, so I was wondering what you're doing for your display testing for Atomic. Have you looked into running any of the Intel GPU tools tests?
No, actually we haven't. We kind of implemented Atomic quickly, and then we forgot about it. So we probably should be doing some testing, and I talked with Daniel even last XDC, and he mentioned these Intel GPU tools, but we haven't actually run those yet.
Yeah, there's been a little bit of progress there on supporting those tests, also being IN15 specific. So I've started running a few of them I work on the PC4 driver for Raspberry Pi. But yeah, it would be really awesome to get more of us working on those tests and making sure that they are runnable on not just Intel, because that's sort of where the development is happening of what are the expectations of this user interface.
Could we run all of them currently, or is there a subset, and is it easy to find out what that subset is?
So I don't know how to find this subset. A bunch of them are depending on IN15 CRC infrastructure, so it's, you know, set up this set of planes, and I expect if you set up this set of planes that this is the CRC of the entire display as that's configured.
Yeah.
I don't have one of those, so how do I get coverage of my display pipeline without that? I think that's one of the challenges we face in trying to get a more generic infrastructure for testing Atomic.
Okay, yeah, that'd be great. I mean, we've been doing some internal CRC testing. That's something we can't release, unfortunately, and it's huge. You probably wouldn't want to see that. But if we could leverage existing stuff, that'd be good.
over here. So I'm just curious, what amount of your abstraction layer is sort of duplicating the DRM mid layer, and what amount would be new functionality? And I guess the follow-up would be, do you plan on pushing that up to the helpers?
So some of the stuff dealing with DP augs and I2C we still have in our code, and we have duplicated. That includes link training because that depends on it. So that, especially the augs and I2C stuff, we've been thinking of ripping that out, but it was never a high enough priority for us, although we'd like to get there. And with that, we could then start reusing DRM's link training and other stuff.
So do you think is your plan still to share the driver across all the platforms, or are you thinking that this is going to make it feasible to do this?
The plan is still to share the driver across all platforms, and what we have in mind and what we've used there a little bit, MSD is one example. We've been using DRM's functionality. We're trying to just have a thin layer we're trying to stay away from layers, but even just a function or a macro that we use to call DRM's MSD stuff that we can then implement on other platforms as well. So it's kind of driven on the DRM side from the requirements there. And that's been one of the things why we haven't ripped out Ox and I2C, because we'll need to implement it on Windows. I mean, we've started bringing up this driver on Windows not too long ago. So that's what I was planning on doing, but we haven't gotten to it yet.
Thank you.
Any more questions?
You've mentioned the white color HDR stuff, and from me as a user perspective, that's what I'm interested in. I want to watch really good movies. And the talk of Andy was about HDR and white color gamut. And did I understand it correctly that you already have this in your driver, or is it coming? Or
we don't quite have that, and I can't talk about whether it's coming or not. Marketing kind of made it clear that's not something I can talk about in this forum. But I think we'd like to work with NVIDIA guys and see if we can come up with something common in DRM that both of us can use. I totally get where you're coming from as a user. I'd like to see that. I'd like to see Linux be on par with Windows, and I'd like to get all the latest technologies, features. Any other questions? If not, then I think Eric has another talk that we're going to go into.
Testing the X server and our process for new contributors. So, confession, I've been playing around with another project that is Servo, Mozilla's Rust-based browser engine. And one of the things that I really enjoyed as a newcomer to their project is just how good their process for testing and contributing is. So what this looks like for them is, you're an interested new developer, you go and fork their repository on GitHub, you clone that repository, hack on it, run the tests, eventually get something that works, you commit it, you push it, And then the entire process for getting your stuff integrated is you go to GitHub and you click send pull request. And you write a little description of what your pull request is. When that pull request comes into Servo, the browser repository, Travis CI immediately picks that up and runs the build and unit tests on it. In the meantime, the core developers, one of them will come along and take a look at your code, and hopefully, if you've done something good, they'll say R+, reviewed by the equivalent on the issue page for that pull request. The neat thing is, once that happens, another little bot called Ors comes along, takes your pull request, executes the merge to the current master, and then runs the full integration test suite. If the full integration test suite passes, then that bot runs the merge to the master. If code is reviewed and passed the tests, it ends up in the tree. Let's compare that to the process we have today for the X server. So a user tries to send us a patch, so they attach the output of get show, and we say, what are you doing? You can't do that. You use get format patch. So they run get format patch and attach it to the email, send it to us, and we say, what are you doing? I can't inline edit, and send you a reply to that. You need to use get send email. Of course, their SMTP server doesn't accept get send email, so they hopefully, if you're lucky, spend a few days setting up a postfix server and fighting with that, and maybe you get their mail in the end, or maybe they just wander off. Even if they manage to send you an email, then it ends up, hello? Okay. It ends up in our inboxes, and if you're lucky, Ajax or Kiki probably reviews it. And if you're lucky, while they are waiting for other reviewers to possibly look at it, they hopefully don't forget about it and never push it. And even if your code eventually gets pushed, the test suite is broken because nobody at any step of the process ran it. So let's fix this process. Step one, let's start building X-Test. It turns out when I went to go build X-Test, it was completely broken, didn't build for the last 6 months. So we fixed that. Cool, let's run it. Well, it turns out that when I had done the infrastructure for running X-Test, I was relying on a local commit that I never pushed, so the framework for running it was broken. Okay, so after we fix the framework too, what does it take to get the X maintainers, the people that are committing your code, to actually run all of these tests? The tests are fairly intrusive. If you run them on your desktop, it's going to spawn a bunch of windows, like 50 new windows. So I can't run it on my desktop. So I made a new little script, XDF piglet.shell, which can be run with make check. It spawns up an XDFD in the background, doesn't take up any space on your screen, and then we run the whole, we run some X tests against it. Cool, so we have software rendering being tested, which hopefully you're never executing. So let's get Glamour tested. That is our GL rendering backend. So this week I sent out Zephyr Glamour Piglet.shell and a bunch of related fixes to get Glamour to start passing the tests. So this one is, I don't want my X maintainers testing to be dependent on my X maintainers environment, right? We're all running different graphics drivers, possibly, or at least on different generations. Our GL drivers are going to be different. I would like all of us to, be in agreement on what passing the tests means. So I spawn XDFB and I run the nested, not XNest, but the Zephyr nested X server running the GL backend on the XDFB, and then I run the X test against that X server. We're kind of into X servers around here. So I now have a system that can make it so that the X maintainers can run the tests. What is there left to do? Well, in that process I was originally talking about that I really liked, there was continuous integration of the patch series. The end user developer got full exposure to the test suite just the same as the core developers did. So I started on a branch to enable Travis CI building of the X server. This is a free as in beer public continuous integration server. So you put a little script in your repository, and when your repository is on GitHub and you've enabled Travis CI, any of your pushes to that repository get tested. That's GitHub only. It doesn't work with our current email workflow. And I don't really think our email workflow works very well for this. Trying to imagine taking patches off the mailing list and constructing a new Git branch from that because we've mangled our Git branches and turned it into email with Git format hash dash capital M where people hand editing them. Can we stop this email workflow thing? I don't like it. What if we had something else? Even if people don't like GitHub, could use Fabricator or something that we're already running that would provide some of the features of GitHub for us. Also to do, as Keith has found out, MakeCheck actually doesn't run this test suite by default even after all my work. I require that you do a clone of Piglet. I require that you do a clone and build of the X test suite. I require that you also build the render extension test suite that I built. And even once you do all of those, I need you to set some environment variables to tell me where you built them so that I can go find them. Could we automate all of this? Could your X server run git clone and automate and make? Could be useful. This is what the process looks like in Servo. When I clone Servo, I clone one of the repositories out of the 100 that are going to be involved, and I type /mock build, and it goes and collects all the repositories, and I run /mock test WPP, and it runs the tests against the build product. I would love something.
Stops working, like that kind of thing. Oh, I lost the hardware even though I still have a DRM context. Why did that happen?
Yeah.
Yeah, the other, in case anyone feels like taking on some easy projects, a large part of the performance slowdown in XTS is because we're doing a lot of image validation. And we're doing image validation by calling xgetPixel once for every pixel. Go look at the xPixel implementation. It is the dumbest thing imaginable. If the X-Test Suite simply knew what images were like and could do things like memcopy, that would be better. It's seriously like the slowest test is doing XY pixmap get image, which is itself slow, but then spending 15 seconds laboriously checking that we got the pixels we expected. Good. So, yeah, X has stupid image formats, and we're bad at testing them. Also, most of XTS's tests, particularly the rendering tests, operate against Windows, which means that they're very difficult to parallelize because with an X server that isn't compositing, you lose pixels when windows occlude each other. So if anyone wants to tease that apart from XTS and make it so we can draw to pixmaps and validate rendering that way, that would be even better. To the things on the message board, yeah, GitLab and Pajur are also possibilities. We have a Fabricator instance on Free Desktop already. And as a server maintainer, I don't like the email workflow. It only became tolerable once I got Patchwork, and Patchwork doesn't work very well. I'm entirely down with, oh look, a pull request. Oh look, here's a branch and somebody added this to a Git hosting system. Yeah, I'm entirely in favor of moving to that kind of model. So you got one vote.
I was about to talk about patchwork indeed, and I fully agree that this is not a good, I mean, the email workflow is definitely difficult for CI, and also it's difficult for people to set up at first. Yeah, but yeah, the patchwork integration can also be done in the meantime, but if the X server could move to patchwork, that would make it way easier.
So we already do patchwork.
I said patchwork, sorry, I meant fabricator.
Ah. All right.
Any other question? Yeah. So I would like to apologize to the people watching the stream for the reboot that happened during this talk, and we tried to fix the audio, but it is better, but it's not perfect yet. And we are gonna reboot again the system, but this side on the presenter side, and hopefully it's gonna fix the audio issues.
Sorry, how long did you say the test suite runs again? Can you go back to that slide?
Let's see. Yeah, a minute and a half for the software rasterizing and 10 minutes for GL on software.
That, if you hook that up, that should not matter. I've got live input hooked up to Semaphore in GitHub, and what happens, it just sends me an email when it's done. So 10 minutes later you get an email, and at least you know, whoops, something broke.
Yeah, this
so
is how my workflow in Servo is
Yeah.
I fire off a pull request, and then sometime later I get a reply of, you know, oh, this WebGL conformance test gave a different result, now you should look at that. And that, you know, I would love for that to be instantaneous or for it to be reliable locally, but, you know, having a centralized server that blesses your results is pretty nice.
There's another thing that just came up in the hallway before. One of the things you can use the test suite for is you can pass the configure minus help output, combine the various without enable this, disable this options, and then just keep running configure, 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 make, so you at least know which version of which configure options will break the build, which is something that we regularly do.
Interesting.
Because someone, you know, not everyone has the same options, but that is something that can just keep running in the background, because it doesn't really matter if that takes a day to run. It doesn't matter if we get the email a day too late that whoops, this broke. It's still better than shipping a server where that combination is broken.
Interesting idea. I haven't played with that.
So I've quick input for people who don't like all the messy merges that GitHub merge request encourage. I know I've heard that complaint from a lot of people who dislike the GitHub merge flow. I recently got some patches into the Flatpak toolset, and they have a workflow that's really similar to Servo that you described, but instead of a merge, at the end, their bot rebases your branch on master and runs the test and then commits it. And if the rebase doesn't work very well, it'll send you an angry email that says, hey, go rebase yourself and repush, and then we'll try again.
Yeah. You know, actually, that sounds like a pretty decent system to me of if your branch being submitted didn't include a merge, then you probably actually intend for this to just sit on top of master and like sit it on top of master and run the test suite and see if it goes.
And then we keep our history readable.
If I get multiple pull requests at once, I will run one of them. I'll pull one of them, run make check, and well, I actually have make check in my pre-push hook now. But I'll do that. When that push completes, I will merge. I'll take that other pull request that I got, rebase it atop the next one, make check that. I try as hard as I can to keep merges out of the history, because I don't care about what your development history was. I care about what X server's development history was.
Yeah.
So there's one thing about email-based workflow. It stores the discussion for posterity and it's distributed in mailing list archives and people's mailboxes, and the other systems are more centralized.
So, I mean...
So you need to take care to preserve the information.
Yeah, certainly if you lost your GitHub issue comments, information would be lost, and that would be really unfortunate. For me as a developer, if you have important information in your GitHub comments that's not in your commit message that I need to know when looking at the history of this repository, then your commit was broken, in my opinion. That said, there is usually more interesting context over there, but it becomes of less interest if you are writing good commit messages, which we're fairly sticklers about.
There's also a review that drops the commit or the patch altogether, and it'll never make to the commit message and repository.
Yeah, that's true and all, but I can subscribe and watch all the, like, on my GitHub account, any tree that, like, if I send a pull request or if I have watched the repository, I get emails for that. We can keep email logs if you want. If we want to have those CC'd onto X.Org Devel, like that bit's trivial.
That would be quite easy.
If that's how you want to read it. Personally, I don't. Like, I hate reading email. I like the notification system in the browser better. I honestly prefer that. And I've got command line tools that allow me to interact with it at the source level. You know, when I'm actually working on the Git project, that's great. But I'm not a huge fan of reading email as a way to interact, because it loses all the things that using a web browser gives you. You the context of, oh, right here, this is where I'm talking about this particular line of code. It eliminates the problem of arguing about, guys, can you please trim the context that you're not replying to when you send an email so I can actually find the one line of comment you made in my 500-line diff. Like, there are real usability improvements from that. If you still want email, yeah, GitHub and all those tools will do it.
I'm not arguing about the review process per se, but I'm arguing that there should be a way to store the information that gets distributed, and you can Google for it and you can find it.
I agree.
Or if you don't care, it needs to be a conscious decision.
I agree for my own sake, and I would agree a lot more enthusiastically if it were clear to me that anybody ever Googled for any previous discussion about what development should look like and what ideas we had and what we were doing. As far as I can tell, that never happens.
Well, it does happen to me at the very least. When you're new to a community and you're trying to figure out why something was this way, trust me, it is very valuable. I guess for you, since you've been following it since, I don't even know how long, a fair amount of time, then yes. But yeah, there are, when you get into a new community, and there are threads basically that are very, very important. And yeah, for instance, I would say the Wentland EGL stream one. And it started as, look, a patch. And if it was stuck on GitHub, then I see the argument. I think that those are all still really post-facto solutions that usually what's missing from those kinds of discussions. Like, yes, okay, we've got tools that will allow us to get full text search and find something about this discussion. What we don't ever have, no one actually writes down the conclusions. There's not a librarian, there's not an editor, there's not somebody writing the journal of, oh, this is why we decided to try this thing, and this is why we decided not to do it. Those conclusions never make it to a finalized closed form. That's something you can actually refer to without having to read the entire thread to restore all the context. So I'm a little... while I consider like, yes, there should be an archive, you should be able to search it, that's good, that's well-intentioned, I think it's missing the point. It's stopping way short of the kind of resource that should be available for new contributors.
And I think one thing that really helps as well that definitely Fabricator does really well, and if I remember right, GitHub and GitLab do reasonably well as well, is separating out the kind of overall slightly higher level review from like down in the weeds of individual diffs. I usually with email find it pretty hard to dig through, and you have to read every single bit of every single review, because you will get high level comments thrown in like halfway through some kind of mega patch. So I think any tool that encourages you to separate those out and keep the overall discussion separate from the bits and bobs is definitely worthwhile.
Okay, we need to make it short now because, yeah.
So just a very brief one. It's for Adam. Do you remember my recent email about direct, indirect? And when you see something like that in the code that contradicts on multiple levels, every sane person will go like, there must be like some discussion about it. And I believe this is the argument Yanni is putting, that regardless of the form, there should be a way to preserve this information. And based on my knowledge, the stuff with GitHub just disappears.
The content of the review stays there forever. You're always capable of going back and finding it. And if anything, it's easier to find that than it is to find a relevant email thread.
Until the server dies.
Yeah, until the server dies, so I remove my commits, which goes away with the comments.
Yeah, okay, let's cut it short. We really are getting a bit late.
Now that I work at Google, I have a different perspective on how some of this stuff should work. Google does things differently, as we all know. So there is a compromise if you want your email threads for high-level discussion, but you want to use your fancy GitHub-like tool or Fabricator. Like one thing that Google does is that all the high-level discussions happen on a real mailing list. It's just a mailing list. It's not a stupid web tool. But Garrett, you don't have to like Garrett, but Garrett is used for the actual code review, and so you can still use your normal mail workflow to go follow the actual discussions and get that archived as you would expect.
Okay, there are questions on the message board. I would say that let's answer them on the message board. And thanks, Spliet, for your work on Dolphin, by the way. Okay, everyone. Sorry for the delay. So what happened with the stream was that basically the audio from the presenter was not available anymore from, well, basically this venue to our system. So sorry in the stream for the people that we had to switch to the mics of the camera, which explains why we had so much reverb and poor volume. I mean, it was still okay to listen to, but yeah, now we are back to full quality. Very good. So I'm going to now continue on the topic of continuous integration, and I'm going to talk about EzBench, the tool that I've mostly been developing to basically improve the graphics stack and improve the testing, and exactly as you were saying, Eric, that we need to know to have immediate feedback, basically automated feedback from machines whenever there's something that is pushed to a branch, and then it has to be tested. Of course, light testing, it cannot have something to complete, and when it is actually tested then it can be reviewed by and merged. Maybe not automatically at first, that would be big change, but of course that would be very nice. And then whenever something is merged, then just because it did work on the pre-merge check doesn't mean that it doesn't conflict with another merge that should happen later. So you need to do proper testing afterwards anyway. And yeah, so there are many challenges with this. So the situation is that we have very complex games and benchmarks that are available and used on Linux by users of all the distributions, and the drivers are getting just as well very complex, and especially as performance improves, you need to add tweaks and all this and multiple code paths, and it's very difficult to test the graphics stack. And users really now rely on open source drivers to run their applications and games, and performance and rendering and everything has to be perfect for them. And even though we have this rolling updating and that may be going on, so the risk when merging code is of course to break functionality that used to work. This is something that is not acceptable. Second one is of course to break the performance of a game or an application, or you may just improve an application and you just tested this before merging everything, but then you didn't test on every platform that it actually improved the performance generally and did not regress something very badly. So it's impossible for a developer basically to have a full knowledge of this. So we need to test and benchmark on all the platforms and games or applications of interest. So the objective of the CI was what I was explaining at the beginning on the intro slide. It really is to, for me, this is my view, and maybe some people would disagree, but the point of CI would be to catch changes in unit test, rendering, performance, or power consumption for a list of tests. And these tests may come from games, may come from actual benchmarks, maybe internal tests, test suites, or unit tests, or it may be conformance testing that is global and everyone has them. So my goal really here is to pinpoint the changes and really figure out what went wrong and where, so as whenever there would be a bug report that would be created, we would have exactly the environment that has been used for testing and the commit that breaks everything. This way you can ping the right author and not just have to go through multiple people who would do bisecting, and they may not have the hardware for it, and basically it just improves the performance. It lowers the impact of the social communication. It's there, and the CI system may not actually even need any human. It can just send an email to the guy who introduced the change and the maintainer. So that's the last part. So, but the challenge is that basically there's variance on everything. Unit tests sometimes may work, like 99% of the time they work, or they report something, and one person is like, no, actually I'm going to report something else. So how do you detect this? Because it may be a change that you added to your code that started adding this this instability, and how do you cope with this? And it's the same with performance. It is not constant. We're going to talk later about this. And even worse, the metrics like power consumption is so volatile. Every run that you make, you have a much different metric at the much different result at the end. It's just like running GLX gears. A 10% variance is definitely possible. Hence why GLX gears is a bad benchmark. Yeah, and since the split of the X server into multiple components, we now have to deal with many components. And you need to update the kernel, you need to update libdrm, you need to update Mesa, you need to update the DDX, and maybe Wayland compositor soon enough. And yeah, how do you deal with this? Because when doing system integration is the sum of all of this. So it has a lot of challenges. And what we really want to avoid is having false positives and false negatives. False positives are really bad because it may prevent code from being merged just because, well, no, the thing doesn't pass. How would I, as a reviewer or the maintainer, I don't want to merge something that doesn't, where all the checks do not pass, right? And false negatives is, I think that everything is fine, but actually not. So it's a lack in your coverage. Or it's just a tool that was like, I'm not sure, so I'm not going to do anything about it. So, yeah. And last thing, it's impossible to test every commit. How long do you think it would take to run all the test suites and benchmarks and games in the world that work on Linux? Well, I don't want to know. So, the current solution that we have for, well, that the tools basically that can be used for CI are the following. So, as far as I'm aware, for unit testing, of course, Piglet is definitely our runner of choice, and also provides a lot of tests. DQP, that is used by Google, is also for glass testing mostly, is definitely very valuable too. There's the conformance test suite for OpenGL or for Vulkan, and I'm sure there are way more internal systems that would be used internally at different companies. For performance, as far as I'm aware, for graphic performance, there's 4NX Test Suite or 6onX that is developed by Ben Vidovsky at Intel. For rendering, I remember 4NX bragging about doing image validation at some point, but I don't see it really happening really often, so it may be because there is some inherent problems, and I think I know why with his implementation. And then, well, recently Eric started working on a tracing system, basically using API trace to trace, to replay a trace and check if the rendering would be different. And this way you can change the versions and then verify always to a database of known good results. And yeah. For job scheduling, well, yeah, PTS also does things, but the biggest one I would say is probably Jenkins, one that almost everyone must have seen in their lives at some point. But the issue with all of these is that they are great for reporting, not for bisecting. The tools themselves do not understand the data they spit out. So there's no feedback loop, basically. And this feedback loop is very important to address the variance. When you have a fail at a certain test zone, then is it because the test isn't stable, or is it because it actually got broken? And unless you start, going back to it and being like, okay, well, maybe since there is a change, I should probably try to reproduce and see if it actually is for just variance issue or if it is a real fail. Also, the environment may have changed if you test before, after, and yeah, but you didn't see that in the background. Your OS just got updated, and you suddenly use a new libdrm that contained a certain problem, or the ABI, of course, is not matching anymore and it just crashes, how would you know, right? So environment is really important. As far as I know, no tool does it. No tool that is in this list does it, properly. Yeah, rendering may be unstable. We're going to talk about this, and so in the end, because of this, I don't want to rewrite all of these, right? That they are very good tools, and I don't want to rewrite all of this. What I want is to basically take care of this variance and get rid of it, or at least rid of it to the extent of the machine time that we have and the data and the certainty or the confidence that we want to have. Okay, and this tool, I called it EzBench. So here is the general idea. So you would acquire data, generate a report, enhance the report, and schedule enhancement. And when you do this, then you request more data that you will reacquire. And let's go through the blocks one by one. So the acquire data block is really about compiling and deploying new versions of, for instance, Mesa, running the test, collecting the data out, so performance or rendering or unit test results, but also collecting the environment. It's really, really important. Then we need to, this acquired data writes the data to the disk or to a separate server, whatever you want to do. Then we can generate a report. That means that basically we read the data from the disk, the data write it down as CSV file as much as possible to make sure that everyone can access it and you can do any kind of operations on it on your own without requiring a lot of tools. So then with the data that has been read from the disk, it creates a Python intermediate representation where you can just query data. I'm like, I would like from this commit, from this particular benchmark, I would like to get the results and for different runs and make whatever operations you want to do with it, or just read the metrics like what is the power consumption and for all the different runs. So that is the report. And from this you can actually start analyzing the data and trying to see like, is there a regression, is there a change or not? And from this we generate events, which is something has changed basically. So it could be performance went down by 10% on this particular game. And this is where the schedule enhancement part comes in. It takes the events as an input and tries to see if it can do anything to deal with it. So for instance, if it needs more run because the variance was too high and did not meet the threshold that we set, for instance like 2.5% variance maximum or uncertainty, or the performance change, maybe, well, we didn't have, it has not been bisected yet. There would be something like 100 commits between the two versions. So what you want to do is probably add a data point in the middle. This way you'll going this way and going through the loop many times, you're going to automatically bisect the change. And in the process it also replicates, which is good. Okay, so the code is on Free Desktop. It is an official project. It's not in my user repo anymore. This change was made at FOSDEM this year, and it's MIT licensed. So the different blocks that we have are the runner, which is bash based, and it handles compilation, deployment of all the different components. It sets up the environment for the tests, for instance running X, selecting the right compositor, selecting the right DDX, and then it does run the test or the tests. So why bash? Because while running tests and doing compilation and all this in Python is no. It's just not appropriate. And writing tests profiles is super simple to do in bash. Then what do we have? The environment dumping. So in this talk I'm not going to talk too much about it because I did talk extensively about it at FOSDEM. So if you're interested in this, you may have a look at the talk, which is also available at in this repo in the folder docs/docs/FOSDEM 2016. But what does it do? It's basically a library that is LD preloaded in the test that you're trying to run, and it dumps all the environment, all the loaded library, any kind of DL open that is made. It's gonna be there and it's gonna log everything. And this is not just for library, it's also whenever you create a GLX context, it's gonna tell you, okay, what context did you get? What version? What extensions were there? For GL it's the same. For X it's what window you created, what size. I mean, you must have seen the issue with, oh yeah, maybe not. But Forenix was testing Zonotic on Windows and Linux, and Windows was so much faster than Linux. Yeah, right. On Windows it was running at full HD, and on Linux it was 4K. Oopsie. But then since there's nothing that actually hooks and checks what is the window resolution, then it was just the parameter that I set was the right one, but then I had no clue if it actually was what happened. So this is really the lowest level you can get the information from, and from there I build up instead of just guessing and trying my best. And it also dumps metrics. So for instance, if you have multiple GPUs on your machine, you want to know which one got used, right? And then after this you want to know what was the power usage of this GPU. Why care about the others? They were not used. Or the temperature for this, or you may also want to know what is the CPU consumption and memory usage and all this, but well, CPU and memory is not yet landed, but the idea is there, and you want to follow the actual power CPU usage of this process in particular, or it could be the memory consumption of this process only. So it's actually way easier to do this kind of things when you are in the address space of the process. Okay, and then you've got report generation, enhancement, scheduling. All this is done in a Python daemon, so yeah, easy enough to hack on. There's a lot of libraries to do any kind of statistics. So yeah, so far this is what I've been using, and it's very easy to hack with. And finally, the reporting is also done by a Python script that generates an HTML file out of the output of the enhanced report. So the features of EzBench, what can it do? Well, it can run Piglet, DQP, IGT, which is work in progress because of the kernel side. We're going to talk about this soon. On the graphics side, it can run basically all the public benchmarks. For rendering, this is very new, so we only support API trace and an internal tracing tool that we have. But this internal one is not public, of course, so we did not put anything there. Then there is the acquiring this environment, what I talked about, this envdump.so. So this is there, and this is good for catching changes. It analyzes variance and data and reproduces changes. So this is that was one of my requirements. And it does auto bisect on data, and metrics is not done yet, which means if your power consumption changes when you, I don't know, for some reason you have a commit like enable power gating, then yeah, it's not going to be caught, and this is not good. So I wanna add support for this, but when I enabled it, because everything is there in the code, it just was too messy and too noisy. So I need to work on the modeling basically. Okay, so what do we support now as components? There is Mesa, and we do not really have limitations here. We can also redeploy the Video Intel DDX. And Linux, we also have support for it, aka it will compile your kernel, it will reboot on it thanks to grub reboot. But sometimes not all commits actually boot. So in this case, the thing just gets stuck, and unless you have an external watchdog, you're screwed. So yeah, so this external watchdog support I do not have yet. So example of variance. So this is an actual variance of, I can't remember which benchmark, but it's definitely a CPU limited one. You can see here that this was supposed to be a benchmark with only one scene, and so in this histogram you can see inside the benchmark, what is the variance for the run? So let's imagine GLXE is running, so you're going to get something like a few thousand frames, and if you dump the frame time for all the frames, then you would get them here. Then here you would get the variance of the average of each run. So let's say you run for 5 seconds, you make the average. That's one data point that would be used for this distribution. So basically it is just all over the place. It's really annoying. We see 3 bumps, basically 3 modes at which it may be operating, and then there's normal variance around these spots. So yeah, this is the kind of variance that you need to take into account, and just saying, okay, well, I'm going to assume a random normal distribution like this one. It's not even normal, but it is more like a normal. Then yeah, you're gonna miss that, and you're gonna do false positives basically in your estimation. Okay, so then what do we do with this information? Well, if you're lucky and it is a normal distribution, then you may use the student t test, which allows you to compare 2 samples or sample set. So in this case, it's sample A and sample B. So sample set. So the blue and the red, and you're basically asking this test: are these 2 distributions likely to be the same or not? And if they are the same, what is the confidence of this? So this is very valuable because when I have 2 versions, on version A I get this sample set, on version B I get this sample set. Is it the same or not? Well, if it is not, then that means there is a change, and then I can start bisecting. Okay, now image comparison. This is something that has been contributed by someone at Intel, Pekka Julha-Ollila. Yep, and the comparison is done between images is done using RMSE, which is root mean squared error. The idea is that, yeah, basically you have 2 images, so if you did the difference, you would get just another 2D image. And what do you do with this, right? So I need to get one number as an output, and this number is basically, yeah, this root mean squared error. This is something that is being used in research. I'm sure there are better options for us. So yeah, this is something that we are keeping open. So what do we do? So let's say that we run on multiple versions, and in this case it's just 2 versions, on version A and version B. We're going to compare 2 frames, and as you can see, in this frame you've got red square, and on the other one it's a green square. Lovely. So there is a change, so that means that the error that is reported is different from 0. So what do? Then we need to acquire more data, we need to reproduce, we need to try again, and on version A actually there is variance. It's not exactly always the same, but it sort of is. And on the version B it sort of is also the same, but yeah, it's still they are still different. So what do we do with this? Well, we're going to generate the average image of version B or version A, and then we're going to compare all the other 4 images to this average image. And then this is going to give us something like this, which is distributions on one axis, which is necessary for the student t-test. And then we're going to apply a student t-test. Ta-dam! And in this case we can see A and B are very close to each other, and of course closer to the average image than C and D would be. And C and D are actually pretty close. So let's imagine that we would have Gaussian distributions that would be up, something like this and something like this. So the mean is so different and the variance seems to be about the same, so it's very likely that it actually is a change. Yep, and this is why you really want to have something like this, because if you did not have this, maybe in version B, you would have had, instead of having this one as you would expect, you would have gotten this one, which is slightly different. So basically it would bisect to every commit, which is not what you want. So yeah, you need to take into account the variance in the rendering. And in most cases it is not necessary, but there are benchmarks like Unigine Valley, for instance, where there is image load store and atomics going on, and the order basically of the threads matters in the output. And we're talking here about, you know, very slight changes. No one would see it, but still is important, you know. And it should definitely not be a false positive. Okay, demo time. Oh dear. Let's see what we can do here. So, first thing I'm going to do is list all the tests that are available on this machine. They are way more available on when you do have more. So this core.sh is the runner I was talking about, and then it just says, okay, well, here are all the tests. So it is, yeah, a lot of them. So what are we going to do now? I'm just checking one thing. Is it big enough? Then is it big enough? Okay, is this big enough? Okay, just getting rid of, oh no, it's okay. So we're gonna say that we want to use Mesa, so we use the profile Mesa. Then we're gonna say that we want to name our report that will contain all the data. We're gonna call it tests. Okay, this is really bad, but whatever. We're gonna run the benchmarks X11 GTK perf. Why? Because it takes 3 seconds to run, which is great. How many times are we going to run it? Once. Well, very, very good. Okay, so let's just, oh yeah, and head is what version of Mesa do I want to use. So we are lucky because I already used head before, so it doesn't need to compile it. It already has it in its cache. So it just runs the thing and it comes back to, it created a new X server. I didn't ask for any compositor, so it did not use any compositor. I just used the default settings and that was it. So it did run the thing and it did return this value. It took 4 seconds. I said 3. Oh dear. So yeah, and it did estimate that it would take 5 seconds to run, close-ish. So then what do? We want to change what compositor is being used, but we also want to change what driver is being used. So let's change the compositor and move to MetaCity, and then we're going to select conf x11 DDX, and let's use the Intel DDX. Okay, so indeed we do have a window now, and it looks like MetaCity. Yep. So the time it takes at the end is actually the time where it looks up all the environment that was dumped, and basically all the libraries, and it tries to find the package that provides this library. So this is why it takes a bit of time. But let's also ask for mode setting, not that we're going to see any difference. Environment diffing. Okay. Well, with mode setting, I don't have anything on this screen. There's a change. Okay. Okay, so what was I supposed to say after this? Yeah, so let's have a look at the report that we can generate. So stats, compare reports, and logs. Name of the thing was test. We generate this. We open this up. I think it's in this browser. And here we go. So we got multiple results. And in the environment, what can we see? So, oh yeah, that would be indeed good. Is this good enough now? Should be. Okay, I'm gonna, yeah. So, basically, all the environment is being dumped. So what you can see is how the binary got launched, and actually that it got provided by Arch Linux, and that the package is named the GTK perf, and this is the version of it, and what, yeah, what that is a 64-bit. It tells you what frequencies you had set for your CPU, and in this case it was basically, yeah, not set to any particular frequency. So then the CPU governor matters, and in this case we use the power save one. Yeah, since it is Intel P state, we can get more information and know if turbo was disabled or not. Yes, it is disabled. That's, if you don't do this, it really is insane, the results. Then what CPU scheduling was actually set, how many processors were installed, the affinity, the niceness, really everything that you can think of, what kernel, what services you connected to, and apparently used, the GTK perf did connect to systemd, pulse audio, the X server, and it tells me how it got launched. Unfortunately, it says unknown version because it couldn't access well, it couldn't make a hash of in memory, because I do hashes of the binary or the library in memory in case it changed on the disk already. I'm being paranoid. And yeah, so it did connect twice actually to X, the 42 one, because it's a good number. And then it did create multiple windows. It connected to this screen, was the composer Metacity. And it did create multiple windows, well, unfortunately a lot of them, but it does give you the size, and if you, yeah, and also when it gets resized, it tells you which ID, so if you have multiple windows, you can check, and to what size, so it's quite nice. Then it also tells you the environment variables that you had set, so apparently quite a lot. And in software, what we have is the boot dependencies, so that is basically anything that would have been, when you compile your binary and add -L, this would be here. So we found libgbm, and you actually can see where I cached the builds. libgl, envdump, and envdump has been, well, actually all of them have been compiled from Git, so they give you the address. In this case, I didn't find the right remote, but in this case it did. So you can see how to basically reproduce this environment. I do not show right now the configure flags, but it is coming. Okay, and for all of these, it is just, yeah, what packages got or exported this. So, well, for dynamic, it's the same, so let's not go there. And there was this OS. I'm sure that no one really cares about the performance of GTK perf, so it's okay if I show you what machine actually used and rendered this. So here it is, the BIOS version, when it was made, the motherboard, the processor, the caches, everything. So yeah, what RAMs, and if they're in the same channel or not, which is very useful if you want to know if dual channel is enabled or not. What memory size. For RAPL, which is the power estimator from Intel, it tells you the limit, so you know what TDP you are supposed to expect. And it checks the number of throttling events on the CPU side, just so we are clear. Okay, so that's the environment. But this, if you did have to check this for every run that you made, it's just impossible. So this is why we want to have a diff of this. And here we go. The only lines that did change in all this are the followings. So this EzBench conf can just be ignored. This is what EzBench has been setting when I said that I wanted to use a certain X server. Well, not X server, X configuration. The command line, how the X server got launched is different. So in this one there was no configuration that was set. In this one it was X.Org Intel. On this one it's X.Org mode setting. And apparently it did not work because I do not see mode setting in here, the X driver, so I should have tested this. But for the compositor, there was nothing that was set before for the first run, so run 0. So none was set, and then Metacity was set. So we do see changes, and we can see also that the resolution did change, so apparently was working when I said that, checking mode settings, so it just didn't see the X drivers, and this is something that is weird, because it should have been, actually, should have been here. Okay, well, it should have tested. Okay, so this is this. Then I'm going to show you how it looks like when we start compiling a version that was not supported before. Fire up TWM and oh, okay, you don't see it. Wait a second. Up. Window 1. and a second window here, just so you can play C-Tris while it's compiling. Well, yeah. So let's stop there. And while it's compiling, we can go back to very useful. Okay, so since, well, we don't want to wait for the 4 minutes that it takes to compile this version on this old laptop, let's have a look at more interesting reports. So this morning I let the machine basically bisect one rendering change that was made on GPU test Pixmark's Volplosion. So I remembered that there was one version between basically now and a year ago, a bit less than, well, exactly a year ago, that did change rendering. And so since I did not remember, I just said, okay, test a year ago, test now, and have fun. And it did bisect. It took something like 12 iterations, and it did bisect to this commit, which we are going to have a look at it soon. And we see here the frame that was the before frame, and this is the after frame. So this is the average image of them, but it doesn't really matter in this case. And we can see here in red are all the pixels that did change, even if it's a slight amount. And the rest is just there as transparent, just to show where basically these pixels are. So it did go through something like 6,000. Wait. Yeah, it did go through 5,000 commits, and it was 7 months, not a year. And no false positives, it just found this one, and good. So let's have a look at actually what it is. So because here we get the information, this is this version, this hash, and this is the name. So I'll just go to cgit and like this, and do basic constant reassociation. So const1 times value times const2 actually should be const1 times const2, make it a constant, and then value. So, well, of course, the precision issues precision changing will affect rendering. And yeah, so all good. Everything is fine. It's acceptable. Then we are going to have a look at a bit something that is a bit more complete. So I ran as a test for developing all this basically. I have one machine that just keeps on running a lot of benchmarks and unit tests and all this. And this is how I catch bugs and all this. And this is absolutely the worst timeline you could ever think about for, yeah, benchmarks. So let's not concentrate too much on this, but we could have a look at, yeah, Manhattan, for instance. So you can see that the performance was sort of stable. Here it's just is commit, not time. So whenever there's nothing to bisect, basically, you would see no data between this. And if there is, if there are no points in between or no lines, that means that another benchmark needed to be bisected here. So it really is bad, and I'm gonna work on this. But yeah, the Google Charts API is fighting me. So okay, but you do see that here there is a big improvement. And let's have a look at this. Sched changed the scheduling heuristic to favor early program termination. Where is Kuro? Well, congratulations! It did improve performance. Very nice. And actually, if I did give the right flags to this report, it would have added a link to the cgit. That would have been nice. And this information was actually in the commit too, because you knew about it. But all is well, and apparently there's another change here that did change performance. And again, Kuro, congratulations. So yeah, but this is what I don't want to do. I do not want to have a look at every machine, every benchmark, and have a look at the improvements or regressions. This is way too much data. So what I want is actually a view like this. I want the tool to annotate the Git history with relevant information. If a commit is irrelevant, I don't care. I don't want to see it. So here it says, okay, on work week 2016-33. Well, I mean, this is an Intel thing, so that's how managers like to see it, so why not? So we can see indeed that there were 2 changes that improved the performance to 3 benchmarks here and 1 benchmark here. So you click here and you can see that, yeah, it was Manhattan 31 and Unigine Valley. So yeah, so this is all well. I did not say which platform it is because I'm not supposed to show benchmark results. So this is unspecified platform and you do not see how I configured it. So okay. You also have unit test changes. Okay, this one is probably a bug actually, but let's have a look at one that makes sense. Okay, implement G blend equation advanced coherent on Gen 9 Plus. And oh yeah, so when I click on it, I see that DEQP has 35 changes and it's skip to pass for a lot of them. Okay, all is well. And for, well, that's basically it. There are some when the variance is not good enough. In this case, this car chase demo, not demo, benchmark. It did run the thing 28 times, and after this, it was still not happy with it, and said, okay, oh no, yeah, requires at least 28, and actually did run 91 times. So basically, it means the variance all over the place. It did not get recognized by EzBench, so it is just, yeah, it's just stuck basically. So yeah, it does get GPU hangs, so of course the rendering performance is a bit unstable. So yeah, that's an example of what you would get. And let's go back to it did not finish bisecting running the thing. Well, it does take a lot of time. I was not kidding. So let's just ignore it. And I need to hurry up a bit. So what are the features that are missing and needed for CI? There's definitely randomized testing. You cannot, as I said, you cannot run every benchmark for every commit or every day. There's just way too many of them. So what you may want to do is have priorities for benchmarks. You have a core set of benchmarks you always want to run, and then some of them, or games, you just, you know, whenever you have time, you just randomly pick one. And then you check with the previous value, the data point that you had, and if there is a change, you start bisecting. It's interesting. So yeah. And test, yeah, should be added randomly as time permits. If you say at 9 AM, I want you to be done, then it's just going to schedule more tests until, yeah, basically it's 9 AM. Well, this 9 AM thing is something that I have in mind. It's not implemented yet. And yeah, this randomized testing is not done either. Then there is supporting multiple changes in components at the same time, aka update your machine, run the benchmark again, and oh, what package actually did change the performance. Yep, funky. So it's gonna be an interesting challenge, of course. But I would like also to to do this, you need to be able to group data per environment and blah, blah, blah. I think we are a bit late, so let's just skip this. Then in conclusion, what do we have? So the goals, as I said, is to annotate the Git tree with changes in unit tests, power or performance, and rendering changes. The goal is really to require as little human intervention as possible and provide reproducible results. So basically knowing the environment, but also soon enough basically give one environment that that you had on your machine, and let the developer get this and feed it to EzBench, and it's going to recompile everything. So of course it won't work for packages, but for the rest it could. So yeah, and this would really help basically QA to be able to reproduce bugs before sending them to developers, or developers themselves could just do it. Yeah, finally, EzBench really tries hard to take care of the pitfalls of benchmarking. So it was the presentation that I gave a year ago at XDC. So not gonna do it again. So really what is important is the environment dumping and diffing. So really to understand what actually happened on the machine. Having reproducible results and trying to handle the variance as much as possible to reduce the false positives and false negatives. Be reactive to changes. By this I mean this feedback loop that allow you to improve basically reports. Yeah, and only when you need it, not if there are no change, why spend time, right? And yeah, it handles most of the testing automatically. So, do you have any question? Okay, we need a mic there.
In the third EzBench slide, you mentioned that for kernel testing, you probably need an external watchdog.
Yeah.
But have you given consideration to the idea of maybe putting that kernel in a Zen virtual environment and forwarding your GPU so that if your kernel goes face down, your hypervisor would still be able to detect it?
I did think about this, but performance impact. So for unit testing, it is good. But yeah. Yeah, it would work for IGT, for instance. Yeah, this is something that could be done. Yeah, for benchmarking, which was the original purpose of the tool, and now it got a bit bigger. I thought that basically it would it would have an impact, and as much as possible, I would rather have no impact. But you're absolutely right. Having developers being able to run on their machine without external hardware is definitely a good thing to have. I also contemplate on using the watchdogs that you can have on your machine, right? I would love to hack grub so as it would set the watchdog before booting, and if the watchdog is not reset after a minute, you know what? Reboot, and grub reboot is going to reboot to the default kernel, and you're all good. So I think this is a better solution because it requires less infrastructure, and having watchdog support for grub is definitely something doable. And actually, the maintainer was definitely not against it. On the contrary. Anyone else? Okay, Consta.
Not a question, but NVIDIA uses something that uses a hidden Markov model for trying if Tegra tests are failing or not. We have dozens of pass or fail tests, and then you get out basically a probability distribution and number that tells how confident we are that this is how often this test fails. So let's discuss about this later.
Well, this is definitely what we want, and definitely the modeling effort of EzBench is not complete, but yeah, I'm only one single developer on this, and I would definitely appreciate if people are really getting kicks out of this could join and improve on this. What I've been really working on is doing the research and development to have the right architecture, and when I have the right architecture, then push for more actually.
Yeah, let's have a chat about this.
Yeah, that would be really nice. Anyone else? Okay, one last thing that I would like to say is that it is definitely easy to install on your machine, whereas other CI systems that I've seen before are basically meant to run on one server or multiple servers, and they need to interact with each other, and good luck trying to replicate this in on your machine. What I wanted is to have QA and developers to use the same tool, and have the tool being flexible enough to handle basically the different configurations. So everything is hook based, and in the profiles basically you can say, hey, instead of compiling the thing myself, please just ask for this particular build bot to do it for you and download it and just deploy it on your machine. So all of this is definitely tweakable, and this is done in Bash, so it's pretty easy to do. Okay, well, thanks a lot.
Okay. Okay. I mean, you can stay here for 2 seconds. Going for the State of the X.Org Foundation update. First thing first, if I can click. Very big thanks to Morten and the entire team here from Intel and Haga Helia for organizing a great XDC once more. So yeah. Come on. Yeah, that sounds better. So yeah, thanks a lot. More serious updates are things we do most are the student internships. We had this year just 2 students, unfortunately. The reason for that is that the 2 folks who've gone out, Martin and Alex, have kind of been sidetracked a bit too much with work. And so we've not been all that dutiful at doing good PR and getting lots of students interested in X and Mesa and Wentland and all these things. So we plan to do better next year and get back to our usual average of around 5 students. I think that was pretty good. And if you want to help, I mean, obviously as a mentor, usually we can find enough, but also just doing PR, very much welcome. The other one was eVoc. We just have 1 student, and we kind of realized that we suck at getting people on board. Essentially, it just magically requires students to figure out how to contribute to projects, and at that point we can pick them up and give them some nice project and find a mentor for them, and that's all nice. But getting your first patch in is something we can't do. And nowadays on the board decided to just put that up as a requirement until someone figures out how to do that better. And I think we need to do better, and efforts like what Eric's started to do with better CI, making the process more discoverable for everyone, documenting everything, hidden assumptions and all these things, so that people aren't just like entirely lost and rage quit after 4 months of trying. That would be really good. Same holds for outreachy. It would kind of be nice to do that, but since that's really geared for complete newcomers, I think as is, we just unfortunately not the right project. But if someone has like way too much time, or just like stuff like Eric, better documentation, trying to get a real outreachy group going on, I think it would be awesome. And we'll definitely support whoever's trying to do something as much as we can from the board. The other bit the board kind of does is trying to find someone to organize XDC, and I can happily announce next year it's going to be in Mountain View in the Silicon Valley, organized by Google. Thanks a lot for Google is here. A few are up there in the corner, and the main organizer is going to be Stefan, who's unfortunately not here. As part of that, we also try to get a bit better at documenting what's required to have a great XDC. So that's all on the wiki. There's the link for the request for proposals process. So in 2 years, it's going to be again in Europe. So if you want to bring XDC to your hometown, oh no. Anyway, so we have a real RFP process nowadays for XDC. Shocking. I guess next big topic is the SPI transition. Like all paperwork, it always takes like 10 times longer than you expect it to, even if you know it takes 10 times longer. But it is well on the way. I think we have some chances of completing it this year, so maybe? I don't know. No, seriously. And big thanks there also to Bruce Harrington, our new treasurer, and Stuart, who was our old treasurer, who are handling all the complicated, tricky monetary stuff. Finally, Foundation itself. We seem to have a bit of sad decline of members, despite that the X.Org community overall as a graphics community is growing. So please become a member. It's like for free, and you can vote on who's going to be on the board and stuff like that. I think it's a good thing. It's kind of umbrella organization organizing or helping to organize XDC and the student internships and all that.
Well, that could be a good one. But yeah, not only members, actually please try to be directors, because we do not get enough applications. So what's the point of electing people when there are 4 slots and there are 4 potential
we have 5.
A bit more this time, but still.
We're trying pretty hard. So yeah. I mean, essentially, like I said in the student intern programs, I think we're not as good as we should or could be, but it takes people to do that. Anyway, everyone here at XDC kind of qualifies. So just go to members.x.org and let me see whether that works. So, here's the link. I should have cloned this. You can click here, join now, and then you can fill out your name here and a few other things that we would like to know. And finally, there's the application statement as to why do you qualify, and you just put it here. Yes, exactly. I was at XDC a whole thing. So please, everyone with your laptops here and not listening to me, this is what you need to do right now. Anyway, I think that's it from X.Org updates. I'm stop boring you and onwards with the interesting stuff. Any questions or stuff or comments or whatever, I guess?
Nothing comes to mind.
There's one. Oh, it's ongoing, and it just takes time, but I think we have all the things covered, and soon, hopefully, everything that's valuable will be held by SPI, and we don't have to deal with taxes anymore, which is an annoyance.
Especially when we forget to file them. And when not everyone is in the US. Okay. Well, let's thank you. So, it is now the time for the GSoC students to present their work. So please come over.
Je t'avoue qu'il y en a qui font un peu plus de pub que vous. Yes. Okay, do you hear me? Yeah. Just before my presentation, I will spoke about the GSoC program. So you said that this year you only have 2 people for 2 students. It's probably because you don't, you're not very integrated in GitHub, because a lot of students search project on GitHub, and there are a GitHub where you can search the community who wants to hire students. So probably you can put your subject on this GitHub. I will find it and send by email. I don't know the GitHub, but
yeah, well, send it to me. Yeah, this would be valuable. There were, of course, more than 2 students who applied. We only selected 2. So I think there was something like 6 people who applied. But yeah, so yeah, it just happened that there were 4 students who wanted to do his project, and we selected him. So that's unfortunate. I think there's definitely not enough advertisement. I mean, usually we just say, okay, here you go, GSoC students, on all the mailing lists. But this, if the people are not already interested in the community, they're not gonna apply. But on the other hand, do we really want people who have no experience at all with the graphic stack, which is absolutely, you know, insane to get in? Yeah, maybe it's also a good filter. So I don't know. This is definitely, we need to try, but yeah, we can try only once a year, and it takes months and it takes time. So yeah,
sure.
Okay. So there you go.
Okay, so this talk is about my work for Mesa. I'm working on the implementation of a FP64 library in a GLSL 1.3. But before speaking about the project, I will speak about me, because you probably don't know who I am. So my name is Elie Tournier. I'm a GSoC student, and I'm also graduate this year for a French French engineering school. And by the way, I'm still available to hire. So let's talk about the project. So Iago, I think I say your name correctly. Yeah. So bring ARB GPU shaders FP64 to Intel to new Intel GPUs. And the stretch goal of my project is to put these shaders for old hardware without FP64 support. So we have to create a library and emulate FP64. So we choose to use GLSL because we can access to the graphic pipeline, and we don't have to write hardware-specific code. And we can also convert this GLSL in IR with the standalone compiler, so we can easily import my code to the Mesa code. And also for the work, I have to use bitwise operation. So the GPUs must be OpenGL 3.0 compatible. Compliant, sorry. So you can find on internet CPU library who do the work. So I choose to convert CPU libraries to a GPU1, and the one I choose is Berkeley Softfloat. So this library is integrated in the Linux kernel, for example, and it's followed the i3 standard. So for the moment, my code is only on my GitHub. I can't merge my code with the Mesa one. For test and debug, I use Shader Runner from Piglit. So with that, I can see if the shader are correct, and like this, we have the unit test for all the function. So an example how to store FP64. So the first code is from the CPU library. So it's just a structure. And for the lib I work on, it's just UVEC2. And I just put an example. So we want to extract the exponential of the FP64. So the first one is just we took high from the structure and just apply a mask. And we can do exactly the same with the GLSL. So we obtain this code. So I do the conversion for every function I found on the CPU libraries, and the function I need to implement the GL, RRB, the GPU shaders FP64. And the plan for the future is to finish to implement the last operation, because I need to implement multiply and SQRT. It's the two functions I need to finish. And after that, I can just integrate the lib to Mesa, and of course just finish to implement RB GPL shaders FP64. So that's it. Here is the reference I use. So if you want to watch to show the library, the CPU one, and you have also my GitHub account. So you can just see the code, review it, you can help it also. So thank you for your attention, and thanks to the board for everything.
Just one thing, you should show them what you, the to-do list that you had
Okay.
with what you did. I think it's on your GitHub.
Yeah, I can find it. Where is it?
So it's okay.
Yep.
Okay, there are all the functions here. So if an easy one, for example, okay, you can see it. Yes. So it's the easiest one probably just negates function. We just toggle the byte sign.
That's not really what I meant. More like you had an overview of what was implemented and what was not.
Oh, I have
something quick. Yeah, probably just go down in the README and that was it.
This one I don't do the README.
But maybe it was as a summary on your website then.
I have one on my website probably.
Okay, we can move to the second talk and then you can finish. You can find it. Okay, let's do this. Up. Here we go.
All right. So
on the other side now.
Well, it will be kind of difficult. So hi, I'm Alex. I was obviously one of this year's GSoC students, and I was supervised by Martin. My work was about a bit-brace OpenGL profiling view. So it's basically an improvement to a bit-brace profiling capabilities and its profiling UI. So what actually what kind of tool was I looking to in my work. There's plenty of software already available for profiling. Things like Intel GPA, NVIDIA Insight, lately it's NVIDIA Linux Graphics Debugger, AMD CodeXL, which got open sourced by GPU Open Initiative. Well, this is a great software and it has a lot of functions, but it's kind of complex, and I just want to do a very simple job to collect and analyze some metrics. Also, what is even more important, all this software has some kind of limited set of available counters, and usually it's also tied to specific vendor. I worked in the framework of APTrace. It seemed like a good idea to add profiling capabilities to APTrace because mainly it's open source. So you should probably know what is APTrace. I probably is the last person here who discovered this tool. But anyway, it's an open source program that allows to record and inspect graphics API calls. So there was already some profiling capabilities available in APTrace before I even have done something. It was about profiling draw calls, each draw call in the recorded trace, and there was some limited set of metrics. So am I seeing blurry, or it's just I? Okay, that's my vision. All right. So there were timestamps, CPU and GPU, so available by OpenGL, and pixels drawn available by occlusion queries, again in OpenGL, and memory usage, but that's, I guess, not very important. So I implemented what can be called a metric abstraction system. So it's basically a system that allows to, in a generic way, to collect different metrics from different sources, from different backends. So, for example, this work I was doing last year, and I implemented such backends as these two OpenGL extensions. So basically, they can be done more work. They can be a backend for PerfKit. Well, I mean for Windows version, and there was a work by Samuel, it was there, which allowed to have similar interface in Nouveau, and some other backends. So you can usually find these extensions available in your drivers. I would say that the first one is more common. It's something like available for Intel Gen 5 till, I guess, 7. So it's not available on the new ones. And it can be found on Nouveau, thanks to Samuel again. So I implemented this system and I plugged it to APTrace via these two command line options. Well, and next problem is that the output of APTrace is basically some table of metrics, so you can export it and use whatever tool you like and whatever methods you have to analyze it, but it's great to have some tool at hand that allows to analyze it. So there was already profiling view available in QAPTrace, that's a GUI for APTrace, and it looked something like this. I won't go into details what is there, so you probably have seen it, and if you haven't, well, now you have. So again, the problem is that it supports only that limited set of metrics, and it's good to have more. And there are also some performance problems because everything was drawn on the CPU side, all these graphs, and with large data, sets, it caused some problems. So I decided to improve it a bit and plug the abstraction system, metric abstraction system, and accelerate it a bit with OpenGL. So my intention was to show a demo, but I guess it will be a bit difficult because all right. So that's an epi trace. I have some random trace opened, and here is the new option for profiling. That's a metric selection interface, so you can either profile draw calls or frames or both. So you can profile frames, that's usually faster, consumes less memory, and well, you can get a pretty good approximation of what is going on. So here are the available backends. I guess this was taken on Intel Sandy Bridge. So that is the old metrics. Oh, it's very hard to do it like that. Here is the Intel Perfmon extension. So you can find some metrics, not all of them are working. Some of them I don't know even what they are. So okay, let's choose them. It seems like, can you tell me if I have succeeded in checking like this one and that one, right? No? Because it would crash otherwise. It's certainly not good. Alright. So here we got frame view. I would like to note that at any point you can add some other metrics. So for example, let's take the same for draw calls again. Just a moment. This one. So usually profiling takes some time, usually a lot of time, but not today. So here we go. That's view of draw calls. So we got a graph view and a table view. We can dock out this view if we don't need it. We have some basic things that you can do with this one, like scroll it. You can note that it's updating like the scale and the granularity of graphs on the fly. So because that's some consuming operations, I mean CPU consuming. Right, you can like zoom in, zoom out, scroll, drag, things like that. You can also have a breakdown on the shader programs, so you can see the codes which were on specific shader programs and pipelines. You have some tooltips. So for example, you can see how many draw calls are on some specific pixel. Right, you can zoom in. Oh, so actually you can do something with it. Next we have a table view. It's not very useful as it is, but you can, like for example, sort it, and then you can group it by something, for example, by program, so you can like then collect some statistics, like for example max, sum sorry, and then you will have a sum for all the calls that belong to specific shader program, which can be useful. For example, you can find a shader program which consumes the most, I don't see it, CPU or GPU, but I mean, you get the point. Well, yeah, that's it. I guess there are some other things, but I probably already taken a lot of time. So, as I said, I was supervised by Martin, and he was very useful. He gave a lot of ideas, and actually the whole idea is initially his, I guess, and I would like to thank him. Also, I could say that this project is basically his. It's basically 50% his great ideas and 50 other percent it's my bad coding skills and
yeah, don't
terrible,
be modest here. You've been great.
Yeah, terrible interface design. Well, anyway, I need some feedback. So in the rare case, if you are interested or you have some feedback, it's very welcome, because I think I couldn't upstream it right now in its current state because it needs some more work and it needs feedback. All right, thank you.
Anyone has a question for him? Okay, then let's go back to Elie. Okay.
Just all the function I was working on. So you can find the function here. If it's finished or not. Sometimes, like for multiply, I just have trouble with the algorithm. I don't know why yet. The link to all the function. Basically, people want me to work on RSQRT, but I don't found any algorithm, and so I try to work on SQRT, and after probably work on a receipt, so we can do stuff like that. Probably. Yeah.
Bring.
So for RSQ and also square root, in the no lowering pass that we use in our driver, because our hardware is awesome and does not provide those. It provides add, multiply, and some other things, but it doesn't provide that. So Kanu wrote this last summer, not this summer, but the one before, a lowering pass in Near that does RSQ, and it's really elegant and nice, and it does it in terms of multiplies, and so it normalizes and then does a square root in regular floating point, and then does some stuff, and then does a couple of Newton-Raphson steps, I think, to fix it up. It's a really elegant little algorithm, so you should take a look at that.
Yeah, I have the link, and I was looking at this algorithm, but for the moment, I'm not sure to be able to work on everything, but I speak with Ian, and he said that it's probably easier to convert the near to the GLSL IR. So I don't want to do near GLSL then GLSL IR. So if we found a direct route, it can be better.
Okay, any other question? Okay, let's thank Elie then.
Thank you.
And I would like to invite our two presenters for the lightning talks to come over in about a minute.
Okay. Just wanted to report back quickly on, give an overview of what we talked about yesterday when we were discussing Unix device memory for several hours. So we've actually made some progress, I think. There were a lot of discussions in the morning especially, a lot of back and forth and ideas being thrown out. And then in the afternoon, I think we started to drill down some actual concrete proposals and get some agreement across, at least people in the room. So hopefully that'll hold up when we share it more broadly. So just a list of the things that we more or less agreed on. We agreed that allocation requests can assert some basic properties of what they're requesting. So things like width and height and format, the app can just supply us, and we'll assume that that's what they want. We won't try to negotiate a width and height for them or negotiate a format, because usually apps already know that they want particular values for these things. There's probably other things we want to assert as well, so we decided this should be extensible. So if you want to say that I want bitmaps in my allocation, that's something else you can provide up front and just provide it as an assertion rather than a request. And then along with these basic assertions, you can provide a list of usage descriptors that describe how you're going to use the allocation. And that's things like I'm going to use it as a sampler, or I'm going to use it as a render target, or a video encoder input thing. Let's see. We decided that allocation property arbitration is based on sets of supported capabilities, which would be intersected. So all these would have to be positive properties, so you could intersect them and receive a set of things that are what remains after you filtered out the impossible ones. And then we'd have a set of constraints that would additionally limit the allocation. And those would generally be union together. So if you had things like your stride has to be a minimum of R, has to be aligned to a certain value on this device and a different value on this device, you really want to take the maximum of both of those to find the minimum supported stride that you can do. And so these would be less general than the capabilities, because obviously how you merge those together is not quite as clear. So that would be baked into the library, how that happens. So constraints tend to be not as generalized as capabilities. So in general, you can think of capabilities as positive things and constraints as negative things. The capabilities can be vendor specific, or the constraints are kind of shared between all the vendors. And that you have to define them in the upstream library. You can't define them in your back-end driver thing. And capabilities can also be general, so there's probably going to be some common capabilities that everyone wants to be able to know how to express. Things like, I don't know, I think stride's a good example. If you're going to do pitch linear allocation, that's something that everyone kind of understands. We don't have to have every single vendor say, I can do pitch linear rendering using this capability, and I have this different capability meaning the same thing. We decided that capability sets are something that should be exposed up to the application level. And they can be something that is serialized and sent across the wire between different processes. And then each side of the or each different process that has them could do incremental refinement on them by passing them back into the library and saying, filter out the ones of these that aren't possible within this process's context and knowledge of the hardware. After you've done all the filtering steps, we decided there's a separate sorting step where you take the remaining sets of capabilities and sort them according to something. So you want to have, given two ways to do the same thing, you want to pick the best one. We did not agree on how to define the best or how to do the sorting necessarily. So there were a lot of ideas thrown out for that, but we didn't really conclude on any one of them yet. So I think there's going to be more discussion to be had there. And then after you do the sorting, allocation would take place based on a single capability set, ideally the best one. Then we eventually agreed, I think, that the new allocation API will be exposed via some centralized library. It's not something like GBM2 or whatever you want to call it, that actually performs allocation and gives the service back. And then I think the key thing is also that API library would have some backend, so you could plug a driver into it, and the driver would be the one that does things like filtering and allocation. We didn't, I don't think we fully closed either on which driver actually does the allocation, but that has to be worked out later still. So there's still lots of unresolved stuff as well. It's not exactly clear how the sorting happens yet, as I mentioned. And then we haven't resolved how to tell the app which state and layout transitions are needed when you're using those images on different in different usage cases that you specified. So if you specify that you want to use an image as a texture and a display surface, you might need to be able to tell the hardware, which one of the cases you're using right now, if you're using one of them or the other or both. So how to do that is not defined yet, or how to tell the app which ones to do or when to do them. We haven't come to consensus on how formats are expressed. So I mean, people said we should just use 4cc. If you have the option, if we could use the Kronos data format spec, but we'll have to discuss that again and come to consensus. We didn't really discuss what type of handle is used to represent the surfaces that this library creates. So at some point we'll have to revisit that. We didn't decide for sure whether or not the new API will have to be able to enumerate devices in the system. And we did not, well, we discussed what kernel interfaces are used for allocation, but we don't know for sure which ones it's going to be yet. It's probably going to be more than one interface, I would think, since drivers might be ones doing the allocation, but we'll have to see. So then, after talking for like several hours yesterday, we decided we kind of reached a point where we have a bunch of ideas, we have some assertions now, we need to go try them out and see how well they work. So people have a bit of homework. There's a long list of notes that capture some of the points here and some more data about them and how we came to the conclusions. I think we need to go test these assertions by maybe writing some toy code and trying it out, some prototypes. People should try to make sure that all the allocation properties they can express in their hardware are expressible as like singular positive values that you can filter out with intersection. We haven't thought of anything yet that breaks that assertion, but there might be some weird stuff out there. And then during the discussion, we came up with a lot of really weird corner cases that can break things, so we had to make sure we talked to those and work them out. So there's probably more of those we haven't thought of yet, so we need to keep thinking about those and point them out and try to work through them and see if they still work. And so finally, I think we had really good discussions yesterday. They were really productive, I think more so than I thought they would be. So we need to follow up those discussions though and keep in touch. I think we had a great group in the room. I want to make sure we can all keep moving forward as we develop prototypes and want to discuss more ideas and as the ideas come up. So I put my email here for lack of a better contact point. If you were in the room yesterday, I didn't take roll or anything like that, so please email me if you can. Let me know how I can get back in touch with you so we can later decide on like a mailing list we can discuss this on, or like an IRC channel or something like that. It should be some kind of public discussion, so I would want to email privately, but I don't think anyone right now, or I don't think everyone that was in the room right now is on the same mailing list yet, so we have to decide where to talk. And then, if you have time, please review the raw notes from the discussion. I'm going to try to clean them up because right now they're pretty non-contiguous and messy. But there's a lot of notes that are a lot of information there and some assertions that need to be tested and proved out. Yeah, so good.
Okay. Well, thank you.
Mm-hmm.
I think he deserves a round of applause. Okay.
Yes? Is my microphone working? It's awesome. These are lightning talks, except not very fast lightning talks. I think James had like 5 or 6 slides. Yeah, so do I. There are only 2 of us. You know, we had lots of lightning slots available. You could have come up with another talk. KRH, what you got?
It's awesome comic relief, so you should let him talk. I have GLX gears as you've never seen them before.
Okay. I'll leave you some time. I started, so I have a little talk on doing some more X security stuff. How many of you know that X has been used in like massively secure environments in the last 20 years? A lot. Yeah. Compartmented node workstation was something we did in X a long, long time ago, and that was like horribly secure with labels on the screens and all kinds of stuff. How many of you have heard of QBOS? Yeah, a couple of you. That's some really interesting work. It really informed one piece of this presentation in particular. Okay, so when you talk about security, you need to talk about an attack surface. X has 3 obvious attack surfaces. You have input, output, and then you have clients talking. So you have the client talking to the user talking to the client, and the clients talking to each other. yeah, basically everything we have in X is a massive attack surface. For input, it's really easy for applications to monitor the input events for other applications, especially keyboard events. With our testing extensions, it's trivial for you to synthesize events for another application. So when you discover magically that your focus is on an X term, you can just synthesize keyboard events and type whatever you want, like, you know, SCP, etc. password to some random URL somewhere on the net. For output, it's really easy to spoof output. We have screensavers that pretend to be the screensaver. They put up, you know, a password dialog. Please enter your password here. Now I can capture your password, even though I'm not actually the screensaver application. We can capture the screen output from any application. Typing your credit card number in, some other application can come in and capture the output. Cut and paste is the hardest thing to solve. For cut and paste, right now there's no way for you to know who is capturing your cut and paste data. So when you select your credit card number to go paste it into your Amazon web page, any other X application in the environment can come and collect that credit card number. You have no way of protecting against that. Similarly, that application could replace cut buffer data so that when you pasted something into your X term, you could be pasting in some uploading of all of your passwords from the network. So that we have a big attack surface, and I have a couple of things on how to fix that. I did some simple security fixes. I posted these before. These are some pretty easy things for us to fix. We can get rid of input monitoring, keyboard monitoring pretty easily by disabling all the testing extensions by default, and getting rid of the key state tracking and delivering events only to the window owner. Those are some pretty easy fixes we can just do. The only problem is if we disable all of our testing extensions, all of a sudden we have no accessibility, which kind of sucks. So we probably can't do that. But the first two are actually pretty easy changes and actually do a pretty good job of cleaning up a bunch of stuff.
But what about hotkeys?
Hotkeys, those are grabbed. Those are not related to these two things here. So a hotkey is something that's grabbed. The other thing I'm thinking about doing is actually doing a little multi-level security thing in X. This is something that we've done before. The X security extension actually does this. It has trusted and untrusted clients, and untrusted clients can do hardly anything. They can't even run the render extension. So nobody uses this because it's not useful today. But in this world, most clients are trusted. And the problem with that is in my world, most of my clients should not be trusted, in particular my web browser, my terminal emulators, all of my LibreOffice applications. I don't want to trust any of those. So I want to make most clients untrusted. But the problem with that is now I have a couple of trusted applications, and how do I distinguish between them? The usual way that we've done that is by having some process come in and label applications. That is a real administrative nightmare. So my suggestion is that we label applications using either a special POSIX user or group, setuid, a setgid application, and have the X server check to see what the group of that application was, or use SE Linux labels on the client process as well. And that way we could automatically categorize applications. In particular, all of my desktop management tools would be setgid to some magic group, or with a magic SE Linux label. And then those desktop management applications would have access to things that regular applications shouldn't have, like grabbing keys on the root window, or selecting for events on other clients' windows, and getting images on the root window, running testing extensions. All these things that normal applications that I want to be unprivileged shouldn't get to do. We can easily just partition them out by making them setgid applications, and that would easily nicely segregate them without a tremendous amount of administrative burden. The reason we haven't used CMW for a long time is that it was a huge administrative pain. How many people run SE Linux on their machines? Yeah, 2? Yeah, exactly. Yeah, on your machine, yeah. So, SE Linux right now is very difficult to set up, which makes it less useful. So I'm looking for something that's very easy to set up, where I can partition my applications into the trusted applications, which construct my desktop, and the untrusted applications, which are all of my user-level applications and that kind of stuff. I think that was the last one. The one thing that I wanted to talk a bit more about was cut and paste. How many of you have even, really thought seriously about the security of cut and paste and the fact that there's literally no protection at all, right? When you select something in any Windows system today, it doesn't matter whether you're running X or something else. When you select that, the application wants to paste that information, tells the Windows system, hey, I want the cut buffer. I want the current selection, right? And the Windows system says, sure, here's the current selection. There's no security at all. If you look at what QBoss does a very interesting requirement. QBoss actually says the user has to make a positive, intentional action that says this client can get the current selection just once. And the way that QBoss does that is with a magic key combination, which is tracked by the Windows system. So that's the only way that you can do a paste in QBoss is if you give a very intentional command. This client is now allowed to get the current selection. And I don't see how we can do anything that is secure which doesn't require that kind of intention, which is to say the Windows system knows that the user intentionally is pasting here, which seems to rule out all kinds of interesting things like when you select the paste in the terminal menu, how does the Windows system know that the user selected a paste item and that the client isn't just lying to it? Right? We have no way of doing that. So I want to have people think about how we can make intentional, non-spoofable pasting activities actually happen in any Windows system.
You know that it has been discussed quite a lot, and actually Microsoft is very good work on this. It's trusted widgets. And we had all these discussions about this a few years ago for Wayland, and I would suggest that you would read basically the mailing list thread.
Is it working?
Well, I'm not saying it's working. I'm just saying it's the right thing to do.
Yeah, obviously. Yeah,
because SE Linux doesn't take into account any kind of context, and Firefox I trust and I do not trust. It's both.
Right.
So the intent is exactly what you mean. It is exactly what should be. And capturing the intent of the user is the hard thing. And are you sure you can manage to do this on X?
Well, QBoss does it with X today.
Well, it's also unusable.
Yeah, agreed. So I'm not saying I have a solution. I have a problem, and I'm hoping that we're going to be able to come up with something usable. And it may be that we have no real way to make it terribly usable. We just need to make it sure that users understand that when they select something, anybody on the system is now free to come and get it. So maybe you don't want to be cutting and pasting credit card numbers or passwords. So
definitely agree.
Yeah. What? Yeah, it's always a good plan. I don't know. I don't have a great other solution. So that was my one last little bit. Does this seem like a reasonable way of separating privileged operations from unprivileged? It's like a simple SE Linux label or set GID thing. I mean, this seems really easy to me.
I just wanted to say, sounds like you'll be making my life even more fun, preventing key gathering on the root window, preventing clip.
No, I'm not preventing any of this. You just have to have a set GID application that does it.
Right.
Okay.
VirtualBox has got to run set GID?
Yeah.
Okay, sounds nice.
Yeah, set GID to, the Magic X desktop group. It's not a big deal. Yeah, that would be the plan.
But let's talk about this later.
Yeah.
There's actually a third one that just added himself.
Excellent.
Third presentation. So if I saw him running around, so where is he? No.
I thought K. Rich was going to entertain us.
Okay, let's wait for him. Yeah, a minute more. He doesn't have any slides, so at least we can unmic you. Oh, well, you're here. Why aren't you speaking? Okay, so.
Okay, thank you. So, hello everyone. My name is Nikolai Kondrashov, and I work at Red Hat currently, but I don't work on anything X related at all. I'm talking to you because I had a project, and I still have it, on supporting graphics tablets in Linux, which is called Digimand. I was working on it for about 8 years already or something, and started with just trying to make my tablet work. So at the moment, the project advertises itself as well, trying to improve Linux support for graphics tablets, but not for Wacom tablets, because that is already quite well supported by the manufacturer and by the community in general. But for the tablets that are, well, more, accessible to people, not so expensive, and especially in developing countries and for beginning artists. So what I've been doing all this time is that I was basically writing drivers for the kernel, which are not that really that big of a deal, because it's mostly HID drivers for USB and mostly just fix the tablet, kind of fix the protocol to make the kernel understand it. The problem with these tablets is that they don't really understand the HID protocol. They try to follow it, but they fail miserably almost every time. One thing or another doesn't work, or buttons don't work, or the pen clicks don't work, etc. And there are also often problems in the stack. Not often, but sometimes, and as most of the users, most of the serious users use Wacom, that is tested, and also developers of the graphical, the drawing applications also test Wacom tablets. They sometimes forget the basic tablets and they stop working. So why I'm talking here is that I found recently that I don't have time to continue working on this project, and I would like to ask everyone here if you'd like to do this kind of work, or you know somebody who would like to do this kind of work, or you know somebody who would like to learn how to do this kind of work, they contact me and I can help them get into these things, and they can learn lots of stuff, starting with contributing to the kernel, understanding HID protocol, understanding how X works, how Wayland works, how the EVDEF system works, and everything. And that is all very exciting, and also you get to talk to a lot of people, to a lot of beginning artists, and what you get is a lot of gratitude. Actually, I haven't heard any complaint through all my time, and also all of the users were very thankful for the work, so it's a very welcoming place to work, and you get very cooperating users. Okay, that's all from me. Thank you.
So I'm wondering if it wasn't actually the end of the conference now. Ta-dam! It is! Well, oh, one more. Well, we do have 15 more minutes. So the requirement of sending slides 30 minutes before. It's okay.
Yeah, let's see if we can. This is I can use this. Yeah. Okay. So first of all, thanks to Jason for letting me use his laptop, and so this is I thought about doing a full talk for this, but I didn't submit one because it's really just a silly side project I had or obsession for a few weeks. But I figured maybe a lightning talk would be a good way to show this, and just there we go. So this is something I'm calling it KSIM, and I've done a bunch of open source things and named projects in the past, and I figured it was finally time to name a project after myself. Right. So I call this is Christian Simulator in the same, and that's probably fine there. Yeah. So it's the same idea as Tom's Window Manager, TWM. This is Christian Simulator. So what we have is thank you. Started with something that we did in the Vulkan project, where the Intel driver has this thing where you can dump all the buffers and the state that the driver produces, and then we can go back and inspect this stuff later with a tool that decodes the ORB file. So ORB dump is a tool that dumps this out, and we end up rewriting it as an LD preload trick. So when you run the driver, you can LD preload this little library in that intercepts all the ioctls into the kernel and dumps out the buffers. So having done that, I realized that when you do that, you hopefully you simulate creating BOs and all the things that the driver does, and then when you eventually get an exec, you have all the buffers, you have everything in the CPU memory. You can just walk through it and look what's happening. So when you get, yeah, that's good, yeah. When you get the exec buff commands, which is where we say, okay, go execute this buffer, we have everything, and we can start parsing through the commands, and we can basically see what the CPU is doing. So doing this, it's not too hard to track all the state changes and everything that the command buffer sets up, and then eventually we get a 3D primitive command. And that's where it gets a little harder, because now we actually have to go and render all the geometry according to all the states that's been set up. And one of the big problems, of course, is that we get shaders from the compiler that is supposed to run and compute vertex informations and fragment colors. So we have to somehow run that. And okay, yeah. So I started out with this disassembler we have for our Intel shader code, and wherever you print an instruction, like we print an add instruction, you could instead of printing it, you could have some registers in an array, and then you can add them by hand. But then once you do this and look at AVX2, you realize that the Intel shader is a SIMD8 machine that works on registers with 8 floats or 8 D words in them, and so is AVX2. So a lot of these things you could directly translate into AVX2 instructions. So you have an add instruction on the GPU, and you emit an add instruction in AVX2. So you can basically translate a lot of the simple stuff directly to AVX2 instructions. Some of the more complicated things are send instructions, which is essentially I/O. If you want to read data from memory, or we want to write a pixel to a frame buffer, or we have this send instruction which goes out and talks to an external function block in the GPU, which does the I/O to memory, does the sampling and filtering, or whatever else is needed to perform that functionality. And that's hard to do in GDIT AVX2 code, so those get compiled to function calls back into the C code. So there is some helper function that gets called from the GDIT code to go sample and filter pixels. And then finally, control flow is not existing right now. That's always the hard part with GPUs, because you have, you actually, typically for branches, you execute both sides of the branch with different execution masks, and AVX2 doesn't really have support for that. AVX 5.12, which is the next version, is available on some Skylakes and up, have mask support, but I didn't want to depend on that. So the plan is to use the blend instruction, which will take 2 registers and take certain channels from the 2 input registers, and then write the output registers according to a mask. So it'll filter. That way you can probably do most of the control flow if you're. But it's not going to be simple. It's all very tricky. And so next step, with this, we can actually compile shaders. And what happens is when we go execute a 3D primitive, we walk through the vertex fetching, which is not too tricky. We pull the floats from the memory and build up the payload for the shaders. And then once we have the compiled shader, we can just run the shader on that payload, and there we have shaded vertices. So that part was doable once you have the JIT compiler. But the rasterizer is a little more tricky, and for me, rasterization was always kind of a black box on hardware. So luckily there are a bunch of really good blog posts out there from Fabian Giesen, who's some kind of expert in this topic here. He has you probably know the blog series, A Tour Through the Graphics Pipeline. That's Fabian, and that's one of the blog posts that I always wanted to read but never got around to. But I can recommend anybody who wants to read that, go read it, because it's amazingly well written, and it gives you a good overview of everything that goes on. He also has a second blog post that you can find from his website that goes into more detail about rasterization. But it boils down to a lot of integer math that is surprisingly simple once you understand these what the edge equation does and how they turn into various center coordinates. And so rasterization is a bunch of exact precision integer math that you can easily extend to do multi-sampling and centroids and all the things that was kind of before I had somewhat intuitive understanding of this, but having written this has been and this is really the main takeaway from KSIM is that I feel that I have a lot more insight in this stuff now. So that was very useful. And rasterization is not a black box. It's a fairly straightforward. But anyway, having done the rasterization step and we can compute barycentric coordinates and all the other things that the fragment shader expects as input, we can use the same jitter to compile the fragment shader and dispatch fragment shaders to write the output. And then at the end of all this, we have a buffer that contains the final image. And one of the tricks in the code that emulates GM is that once we are ready to send this buffer to the X server, we can on the fly create an actual VO from the kernel driver with the user pointer. This is this ioctl that Chris Wilson added that lets you take a random memory range and turn it into a buffer object, and we can then pass that to the server, the X server or compositor, Wayland server on fly, and that'll then get presented by the Windows system on the system. So at the end of the day, you can basically run. Yeah, okay, it's all on GitHub. KSIM. If anybody wants to go take a look, but I'm not working on it so much these days. But it was a fun project for a few weeks there. But let me try to run a quick demo. So of course there is one application that has to work, GLX gears, and I'll get it over here. This is coming. It's on its way. There we go. GLX gears, and it's flickering there because of course the software rasterizer has no way of synchronizing with the hardware. It just renders, and then the hardware eventually copies from the buffer. So sometimes we race with the clearing of the buffer. And the frame rate is surprisingly good. I mean, again, the rasterizer is running, it's a parallel rasterizer. It uses SIMD8 for rasterization as well, so you can step through the pixels, and with a few CPU a few AVX2 additions, you can determine whether 8 pixels are inside or outside the triangle. So it's a fairly efficient rasterizer. Yeah. And so it has a bunch of options that lets you see what it gets decoded. Well, it's interesting because since this hooks in at the I/O control level, it's completely API agnostic. It doesn't matter if you're running GLES 1, 2, or 3, or full GL, or Vulkan. So if you wanted a Vulkan rasterizer, software rasterizer, you could finish KSIM and then run Vulkan on top of it. But it may be faster to just write a Vulkan software rasterizer in the first place. But and also this runs under Wayland because Jason's running Wayland here. But if you're running under X, it wouldn't care because it hooks in and hooks the ioctl and eventually creates the. Well, it would need DRI3 because we pass prime FDs, DMA buff FDs to the server. So that's the requirement. Well, let me try to run this without the quiet switch here. So there's a lot of stuff that gets dumped here. Let me see if I can stop it with something interesting. Okay. Let's see. Okay, so here's some interesting stuff. This is a jitter doing the vertex shader. So, well, first up here we see tracking some of the command buffers. We set up the constant buffers, binding tables, and steam out. Okay, that should have been stream out. That's funny. No, I know what a stream out is, but steam out, I don't know. I guess we want to blow some steam here or something. Okay. Anyway, this sets up the pixel shaders, and so once all this is done, we go and there's the clip viewport. But here comes the interesting part. This is the vertex shader getting compiled from the EU GPU instructions. Here gets compiled into these AVX2 instructions. So this basically shows the jitter at work here goes from GPU and then the AVX2 instructions here. And so that gets decoded, and this shows the when we're actually running, we load vertices in and set them up like vertex ID 0, 1, 2, and so on. And ultimately, we have enough vertices to run a SIMD8 vertex shader, and it then eventually writes this output here. So, yeah. Anyway, so that was probably gone over whatever short time I had, but it was a fun project, and it I think I got to the point where it runs GLX gears, so I'm done. And that's one relief of having a project like this is that Intel already has a simulator that is very useful and in use, and to do this is it's going to be like maybe 2 years to get this finished and useful. So it's kind of nice to have a project that we upfront just accept that it's never going to be useful or complete, so you don't have to worry about releasing or anything. So it's just a sandbox for crazy ideas. Tessellation, well, you get to work in Vulkan first, and then maybe I'll update KSIM. All right, that's it. Thank you.
Okay, so this time it really is the end of the conference. So thanks a lot for participating and attending the 3 days. I would also like to thank Intel, because not only did Intel pay basically for my engineering time, and I managed to work on the XDC organization on my work time, and also Daniel Vetter got some time off for this too, so that was really good. But also Intel paid for the catering, so you should be thanking for all the coffee and pastries. And, well, I think that's it. Now I'll just have to go and timestamp all the videos. Lovely. Thank you very much again. Bye-bye. Oh no, I forgot one thing. Let's also thank the AV team, who's been doing a very, very good job. And of course Haga Elie for sponsoring well, this room basically, and Tuomo, who was the organizer on this side. So again. And I cannot come up for a new reason for you to clap, so yeah. Hey, I did forget to talk about something. The social event tomorrow. So what's happening there? So we're going to go to Mainline at 10 a.m. And then we're going to just walk there for a few hours, come back to the center, eat something, and then we're going to go to basically a sauna. And next to the sauna is the sea. So, yep. So everyone registered. Actually, even if you did not register, it's fine. We didn't actually need to make any kind of reservation, which was really good. The price for the sauna was something like, it was 9 plus 6, so yeah, probably 15 euros, let's say, or either 15 or 12. I can't remember. So that's about, how much is it? Say again? So we would meet in Kaupatori, so I would say, I know that you don't know where it is, so just check out the program and I'll put a Google Maps link, okay? At 10, I already said.